Hi everyone, welcome to goclasses. Before we start this session, please let me know audio, video, volume, echo, is everything perfect? Is everything clear? Let me know. All good? Okay, so everything is fine. So let's start. So, hi everyone, welcome to goclasses. My name is Deepak Punia, and in this session, we are going to discuss AIMT 1 All India Mock Test 1 solutions, detailed solutions. So, basically, for GATE CS 2026 aspirants, goclasses conducted AIMT 1 All India Mock Test 1, and in this session we are going to discuss it. Before we discuss the questions of AIMT 1, let me thank all of you. So you can see here that almost 3800, almost 3800 students attempted AIMT 1 live. Okay, so you can see that this is Go classes AIMT 1 GATE CS 2026, and you can see this is the number of students who attempted live. Okay, and this is close to 3800, almost 3800 students attempted live, and I want to thank all of you. So thank you for your trust in Go classes, thank you for your trust in Go classes courses, test series, mock test, AIMT all India mock test. So thank you for your trust, and I hope that you loved it. Okay, basically we have put a lot of efforts creating the questions of this All India Mock Test 1, and similarly we will put our best efforts in AMT 2, 3, 4, 5. Basically in all the All India Mock Test we will put our best efforts, and I hope that you loved the experience, you loved the quality of questions, you enjoyed the test, and most important, that after the analysis of the test you learn something new. Okay, you improve a lot. That is the purpose of all the test series, that is the purpose of all the all India mock test. So that is the purpose of mock test. How many marks you are getting, that is not the purpose. Okay, if you are getting very good marks, if you are getting low marks, that that is irrelevant, I can say. Okay, the most important thing is that you do the analysis of the test and you improve. Okay, keep improving. After every test, you keep improving your knowledge, you keep improving your understanding, and you become a gate topper. Okay, and you can see here that this year AIMT 1 was attempted by almost 3800 students live. And let me tell you that last year this number, you can see I have put here, last year for gate CS 2025 aspirants, you can see this was AIMT 1, All India Mock Test 1 last year, and it was attempted by live. It was attempted by 2485. Almost 2500 students attempted last year live AIMT 1, and this year almost 3800 students attempted AIMT 1 live. Okay, you can see the difference. Also, you can see almost 1300. Okay, almost 1300 students. That is the difference. This year, I can say more students have attempted AIMT 1 live. Okay, so I hope you loved the vibes. Okay, you got the actual gate vibes. You are attempting the mock test, simultaneously with 3800 students all over the India. 3800 students are attempting the same test which you are attempting. Okay, they are also solving the same questions that you are solving. So I hope you got some kind of, I can say, the actual gate vibes. Okay, and also the quality of questions, I hope you loved. Let me also tell you, this is the GATE CS All India Mock Test schedule. You can see for GATE CS 2026 aspirants, this is the schedule of All India Mock Tests, AIMTs. You can see this AIMT 1, this is already over. And every Sunday, we have All India Mock Test for GATE CSE 2026 students. You can see the next Sunday, 28 December, then the next Sunday, 4 January, then the next Sunday, then the next Sunday. Okay, we have All India Mock Test. All these All India Mock Tests, they are free for all the students. Okay, they are free for all the learners, they are open to all, they are free for all. Okay, so attempt all the all India mock test, and after every test, test by test, you keep improving and you become a gate topper. And let me share with you the go classes gate da AIMT schedule for gate CS 2026 aspirants. These are the AIMTs all India mock tests that we will conduct. You can see every Saturday from 27 December onwards. Okay, basically the next Saturday, 27 December 2025. Okay, so you can see we have gate da all India mock test 1. Then you can see every Saturday we have all India mock test for gate da aspirants. Okay, now let's start the solution session. In this session we are going to discuss all the questions of AIMT 1, all India mock test 1, and detailed and complete analysis we will do in this session. Okay, let me just quickly go through your chat if you have any doubt. Of course there are a lot of messages in the chat, so I won't be able to see all of these messages, but definitely I can see many good messages. I can see here students are saying that they loved the all India mock test 1. Okay, high competition. Let me tell you, in the gate exam also the competition is increasing, that you already know. Okay, but the the actual gate vibes you can get before the gate exam, you can get in go classes all India mock test. Okay, and you can see the first AIMT 1, this was attempted by 3800 students live. And AIMT 2, 3, 4, 5, so maybe the number will increase and it may get closer to 4500 or maybe 5000. Okay, so basically before the gate exam, if you want to do the rehearsal, okay, how to handle the pressure of the gate exam, okay, basically to reduce the silly mistakes, for the time management, okay, for learning, for improvement, for analysis, okay, basically for all these purposes which will make you a gate topper, for all these purposes you should attempt each and every AIMT of go classes. Okay, now let's start the solution session. One by one we will discuss all the questions and the complete and detailed analysis we will do for all these questions. Let's start with this question. This is a theory of computation question based on closure properties. What is the answer? Tell me your answer in the comments. Which answer did you mark when you attempted the all India mock test 1 for this question? Tell me what is the answer. Okay, let's solve it. This question is asking which of the following statements is or are true. The question is asking for true statements, and this is a MSQ question. So one or more than one options can be correct. Okay, you can see the union of two context free languages is context free. Yes, this statement is true. The context free languages, they are closed under union operation. So when I have CFL1 union CFL2, and if I take their union, the union of two CFLs, that will always be a CFL. Okay, so you can see that CFLs, context free languages, they are closed under union. It means that union of two CFLs will always be a CFL. Very simple. Let's see the statement B. The union of two context free languages is not context free. This statement is false. This can never happen. The union of two context free languages is not context free. This will never happen. Okay, the union of two context free languages will always be a context free language. Okay, the question is asking for true statements. So far option A is true, option B is false. What about option C? The intersection of two context free languages is context free. The intersection of context free languages, that is context free. This statement is false. The context free languages are not closed under intersection. So the intersection of two context free languages is context free. That is not necessary. Okay, so this statement is also false. What about statement D? The intersection of two context free languages is not context free. This statement is also false, because remember, the intersection of two context free languages may or may not be context free. We already know that context free languages are not closed under intersection, but that does not mean that intersection of two context free languages is non context free. Okay, remember, when we say that context free languages are not closed under intersection, it actually means that the intersection of two context free languages may or may not be context free. We cannot say that intersection of context free languages will be non context free. Okay, this we cannot say. So remember, this option, this statement is also false. So for this question, the answer will be option A. I hope you understood. Now let me tell you more about this option D, because I have seen many students they made mistake in option D. Many students, what they think, they think that okay, intersection of two CFLs, CFL intersection CFL is equal to non CFL. This is what many students think. Okay, but let me tell you, this is actually wrong. Okay, this is actually wrong. Let me tell you that CFL intersection CFL, if you have two CFLs, for example, CFL1 and CFL2, you have two context free languages, and if you take their intersection, then remember, the result may or may not be context free. The resulting language may or may not be CFL. Okay, and because the resulting language may or may not be CFL, that is the reason we say that context free languages are not closed under intersection operation. Let me give you example. Consider the first example. I am giving you two CFL. Okay, consider this CFL a power n, b power n, where n is greater than equal to 1. This language is a context free language that you already know. Okay, let's consider another context free language, that is a power n, b power 2n, where n is greater than equal to 1. Okay, both these languages are CFLs that we already know. Okay, yes or no? So you can see that this language is also CFL. This language is also CFL. But what is their intersection? Their intersection is phi, empty set. And this empty set is actually regular, and every regular language is CFL. Okay, so I can say that the intersection of these two CFL, that is actually a CFL. Okay, but of course, I can give you another example where the intersection of two context free languages will be non context free. Okay, for example, consider this example a power n, b power n, c power m. Okay, intersection a power n, b power m, c power m. Okay, consider this intersection of these two CFLs. Here you can notice that this language, this is also CFL. Assume n comma m, they are greater than equal to 0. And remember, in the theory of computation subject, when this is not given, what is the range of these power variables? Okay, see these variables, you can see n comma m, these variables are in the power, right? Okay, so these variables which are in power, if their range is not given, then by default it is greater than equal to 0 in theory of computation. Okay, so here n comma m, they are greater than equal to 0. Okay, here you can notice that this is also CFL. And what is the intersection of these two CFL? That is a power n, b power n, c power n, which is a famous non CFL language. This language is actually a famous non CFL language. Okay, I hope you understood. So very simple point, remember that intersection of two CFL may or may not be CFL. I can give you many counter examples. I can give you, for example, consider this phi. This is a regular language, so yes, this is a CFL also. Every regular language is CFL. Consider intersection with any CFL you can take, CFL2. Okay, now you can notice what will be their intersection. Intersection of any set with empty set, that will be empty set. And you can see what is this is regular, so yes, this is CFL. Okay, so here you can see that intersection of two CFL may be CFL, and intersection of two CFL may not be CFL. Okay, so finally I can say that intersection of CFL, the intersection of two CFLs may or may not be CFL. So you cannot say that intersection of two CFL is CFL. Also, you cannot say that intersection of two CFL is non CFL. Okay, so finally for this question, the answer will be option A. I hope you understood this question. How many of you did this question correct? Can anyone let me know? Did you learn something new from this question? One thing I can tell you, if you did this question wrong in the AIMT 1, then that is a good thing, because you will not make it wrong in the gate exam. Okay, from this question, from the analysis of this question, I hope you understood some concepts, you learned something new, and I hope that you can feel the improvement, that yes, some knowledge has improved. Okay, maybe it will help in the gate exam. In the gate exam, if similar question comes, then you will be able to correct it. Okay, you will not make it wrong in the gate exam. Okay, that is the benefit of making some questions wrong in the go classes AIMTs or go classes mock test or go classes test series. Okay, is this clear? One student is saying in the chat, one student is saying, but sir, according to may or may not statement, C comma D can be correct. Let me tell you, whenever you are solving the question, all the options you must consider them individually. Okay, remember, when you have four options and if you are checking the true or false for four options, then remember, every option you have to consider individually. It's not like, okay, that this is a single option. Okay, this is not a single option, that this is a single thing. No, this is a different option, you have to consider this individually, and this is a different option, you have to consider this individually. Okay, so don't make mistake. Now let's move on to the next question. Let me know this question, this particular question, in which category you will put: easy, moderate, or hard. I think this question is easy concept. The concept is actually easy once you understand it. And remember, again, I am telling you, in the theory of computation, when you say not closed, when you say not closed, what it actually means? This actually means may or may not. Okay, basically, when you say not closed, it basically means may or may not. Okay, most of the time. This means may or may not most of the time. Okay, this means may or may not most of the time. What I mean by most of the time? Okay, notice one thing. If I say that regular languages, yes, regular languages are actually closed. Okay, so they're nothing. Okay, yeah, so basically I'm saying that whenever you use this word not closed, then most of the time it will mean that, okay, may or may not. For example, if I say that intersection of CFLs, the CFLs are not closed under intersection, it simply means that the intersection of two CFLs may or may not be CFL. Okay, I hope this point is clear. Now let's move on to the next question. Let's solve this question, discrete mathematics graph theory question, a very beautiful question. I hope you loved it when you solved it. So the question is saying that G is a graph. G, V, comma E. V is the vertex set. This E, this is the edge set, and this is a simple connected non-Eulerian graph. Non-Eulerian graph means this graph is not Euler graph. Euler graph, Euler graph. Okay. Basically, there is no Euler circuit. You can say whatever is the correct pronunciation, Euler, Euler. Okay. So let's call it Euler. Okay. So you can see that this graph, this is a simple connected non-Eulerian graph. Means in this graph, there is no Euler circuit, there is no Euler circuit. We want to construct a graph, not necessarily simple. Read this. A new graph we want to construct, which may not be simple graph, that is Eulerian, that contains G as a subgraph. Basically, this G, on top of this G, we want to, on top of this G means we want to add some edges, some vertices. Basically, this G must be a subgraph of H. This H, this new graph H I want to create, which is Eulerian. Consider the following possible construction processes. Now, 5 possibilities are given, and we need to find which of them will always correctly create a Eulerian graph H. Okay, my purpose is to create a Eulerian graph H, because this graph G, this is non-Eulerian. Okay, and I want to create a new graph. This graph H I want to create, which contains G as a subgraph, and also this H is Eulerian. So these five possibilities, these five possible solutions are there, and we need to figure out that which will guarantee, which will correctly, which will always correctly construct this graph H. I hope you understood the question. Now let's solve this question. First of all, you notice, if this graph G is non-Eulerian, what it actually means? You already know, a simple graph, a simple connected graph is Eulerian if and only if every vertex has even degree. Yes or no? this theorem, this theorem we already know that a simple connected graph, a simple connected graph is Eulerian if and only if and only if, remember this is if and only if theorem. So a simple connected graph is Eulerian if and only if every vertex has even degree. Every vertex has even degree. Okay, is this clear? And one more thing you remember, there is another theorem. What is that? That is that in any simple graph, whatever simple graph you take, in any simple graph, the number of odd degree vertices, that is always even. Yes or no? Okay, so we already know that in any simple graph, actually in any undirected graph, whether simple graph or non-simple graph, in any undirected graph, whatever undirected graph you take, simple or non-simple, so basically in any undirected graph, remember the number of odd degree vertices, how many odd degree vertices are there, whatever undirected graph you take, then the number of odd degree vertices, that is always even. How many vertices can have odd degree? That is even number of vertices. Okay, means whatever undirected graph you take, always it will happen that even number of vertices have odd degree. The number of odd degree vertices is always even. Now tell me one thing. Here the question is saying that G is non-Eulerian. So what can you say about it? How many odd degree vertices G has? Can you tell me? Very simple question I am asking. G is non-Eulerian. G is simple graph, connected graph, but G is non-Eulerian. So can you tell me how many odd degree vertices G has? How many odd degree vertices are there in G? Tell me. So you can see, because this G is simple connected non-Eulerian graph, it simply means that not all vertices have even degree. Yes or no? The graph is not Eulerian. It simply means that not every vertex has even degree, because if every vertex has even degree, then the graph will be Eulerian. Okay, yes or no? I am talking about simple connected graph. So for simple connected graph, we can say that if every vertex has even degree, then the graph will be Eulerian. If you are saying that the graph is non-Eulerian, then definitely we have some odd degree vertices. How many odd degree vertices will be there? Number of odd degree vertices is always even. So can you have one odd degree vertex in this graph? Can you have one odd degree vertex? Can you have three odd degree vertex? No. The number of odd degree vertices is always even. So I can say that in this graph, I can say that G has at least two. G has at least two odd degree vertices. At least two odd degree vertices. Okay. So what will be the number of odd degree vertices in G? That will be 2, 4, 6, like that. Okay. So if you see what will be the number of odd degree vertices, because this graph is non-Eulerian. Okay, because this graph is non-Eulerian, so I can say that number of odd degree vertices in G, that will be what? That will be 2 or 4 or 6 or 8 or and so on. Basically I can say that even number, some even number which is greater than equal to 2. Okay, I hope you understood this. Very simple so far. Two easy theorems we have understood. Now let's solve this question. In this question, some solutions are given. How to convert non-Eulerian graph to Eulerian graph. And this new graph that you are getting, this may not be simple. Okay, so let's see here which solutions are always correct, which solutions will always work. So let's see the first solution. The first solution is saying that add a new vertex connecting it to every vertex of G by an edge. This is the first solution. This is suggesting, okay, you can see the first solution that we are suggesting, that is we are saying that add a new vertex and you connect this to every vertex of G. Will it work? It may not work. Let me tell you, it may not work. It may not work. And the question is asking which solution will always work? Which solution will always correctly construct a Eulerian graph H? Okay, and remember this Eulerian graph H, This must contain G as a subgraph. So from G you cannot remove any vertex. From G you cannot remove any edge. Okay, is this clear? Okay, you can see contains G as a subgraph. What it actually means? It means that you cannot remove any vertex from G. You cannot remove any edge from G. Okay, you can add vertices, you can add edges, but remove you cannot remove vertices or edges from G. Is this clear? But yes, you can add vertices, you can add edges, that you can do. Okay, now let's see this first. So can I give you a counter example for this? For this option A, you can see I can give you a counter example that will be like this. Consider a graph like, for example, A, B, C, D. Consider this graph. Now in this graph you can notice that, okay, let's consider this graph. Okay, let's consider this graph. Now in this graph you can notice that the degree of this vertex C, that is 2, the degree of this vertex D, that is 2, the degree of this vertex A, that is 3, the degree of this vertex B, that is 1. Now what this A is saying, this is saying that add a new vertex and you connect this vertex to every vertex of G by an edge. So for the new vertex, what will be the degree? I am adding a new vertex. A new vertex I am adding. Okay, this was my graph G. You can see this is the graph G. Okay, now you can see what I'm doing. The first solution. The first solution is saying that we are adding a new vertex. This new vertex V we are adding. Okay. And what we are doing? We are making it adjacent to every vertex of G. Okay, yes or no? You can see that we are connecting this new vertex to every vertex of G by an edge. Okay, by one edge. So you can see this is what we are doing. Now can you tell me what will be the degree of this new vertex? That will be the number of vertices in G. Yes or no? So you can see the degree of this new vertex, that will become 4. Now let's check the degree of the remaining vertices. Okay, you can see now here the degree is 2, here the degree is 4. Okay, here the degree is 3, and here the degree is 3. So notice one thing, that again, not all vertices have even degree. So this is also non-Eulerian. Okay, this is what you got. This H you got, but this H is also non-Eulerian. Is this clear? This G is also non-Eulerian, because the question is saying that you take a non-Eulerian graph and we need to convert this to Eulerian graph. But here you can notice that if I apply the solution number 1, then it is not necessary that I will get a Eulerian graph. Yes or no? Here you can see that not all vertices have even degree. So this new graph that I'm getting, that is also non-Eulerian. So definitely I can say that this first solution may or may not work. Okay, or I can say that the first solution will not always work. What is the problem in the first solution? In the first solution, the new vertex that you are adding, what will be its degree? Can you tell me? This new vertex, for this new vertex, can you tell me what will be the degree? What will be the degree of this vertex? That will be equal to number of vertices in G. Yes or no? Very simple point, that in this solution 1, notice one thing, that the new vertex that I'm adding, this new vertex, degree, what its degree will be? For this new vertex, the degree will be number of vertices in G. Now notice one thing, in your graph G, if you have odd number of vertices, if number of vertices is odd, then also you can notice that in the new graph, this new vertex will have odd degree. Okay, so definitely I can say that this solution 1 may or may not work. It will not always work. Very simple point. Okay, let's see the solution 2. So solution 1 is not always correct. Okay, and what about the solution 2? Let's see the solution 2 here. The solution 2 is saying add a new vertex connecting it to every vertex of odd degree in G by an edge. Okay, now the question is saying that you have this graph G. Okay, and in this graph G, from this graph G, the second solution is saying that we add a new vertex, but we connect it to odd degree vertices. Okay, like odd degree vertices, odd degree vertices. So this new vertex that we are adding, we are making it adjacent to all the odd degree vertices of G. You can see that add a new vertex, connect it to every vertex of odd degree in G by an edge. Okay, by an edge. So now you tell me, if we do this, then what will be the degree of this new vertex? This new vertex that we are adding, what will be the degree of this new vertex? Can you tell me what will be the degree of this new vertex? First of all you can notice that this graph G, this is non-Eulerian, simple connected non-Eulerian. Okay, simple connected non-Eulerian. Okay, and after this second solution, means I am adding a new vertex, and I am making it I'm making it adjacent to all the odd degree vertices of G. Then this new graph, this also will be connected, because the old graph is connected, and we are just adding a new vertex. We are making it adjacent to every odd degree vertices of G. So this is also connected. Yes or no? This new graph that you got, this is also connected. Okay, very simple. And you tell me, for this new vertex, what will be the degree? Because we are making it adjacent to all the odd degree vertices of G. How many odd degree vertices G has? Number of odd degree vertices in any undirected graph, that is always even. Yes or no? So you can see in this G, the number of odd degree vertices, that is even. And this new vertex, I am making it adjacent to all the odd degree vertices of G. So definitely this new vertex degree will be even. Okay, yes or no? So in this new graph that you are getting, this new graph as that you are getting, in this new graph, you can notice that this new vertex will have even degree. And notice one thing, that all the previous odd degree vertices, their degree is increasing by 1. Yes or no? Plus 1, plus 1. For all the odd degree vertices of G, for every odd degree vertex of G, now the degree is increasing by plus 1, plus 1. Okay, so you can see now all the previous odd degree vertices of G, now they have become even degree vertices in H. And remember, all the even degree vertices of G, they are, as it is, they are unchanged. So I can say that in this H, every vertex has even degree. Every vertex has even degree. Yes or no? I hope you understood this point, that in this graph, in this new graph that we have created, in this new graph H, every vertex has even degree. The new vertex that you are adding, that also has even degree. Okay, and all the previous odd degree vertices, their degree has increased by plus 1. So now they have become even degree vertices. And also all the previous even degree vertices, they are unaffected, they are unchanged. So I can say their degree is also even. So in this new graph, every vertex has even degree. And this new graph is connected, every vertex has even degree. So definitely I can say that this graph is a Eulerian graph. This is what we want. Yes or no? So definitely I can say that the second solution will always work. Okay, it will always correctly construct Eulerian graph H. That is what we want. Okay, now let's see the third one. Let's see the third solution. The third solution is saying that create a new copy G dash of graph G and add an edge connecting each pair of corresponding vertices. Notice, we need to create a new copy G dash of G. Duplicate copy we need to create for G. Okay, and what we need to do? We need to add an edge connecting each pair of corresponding vertices. Like for example, A to A, B to B, something like this. Okay, is this clear? This is what it means. So tell me, will it always work? This third solution, will it always give me Eulerian graph? The answer is no. I can easily give you a counter example for the third one. Notice, in the third solution, what you are doing, you have a graph. Okay, for example, take any graph like this. Okay, A, B, C, okay, D. Now consider this graph. In this graph, you can notice that this vertex has degree 2, this vertex has degree 2, this vertex degree 3, this vertex has degree 1. So because not all vertices have even degree, that is the reason this graph is non-Eulerian. Okay, not all vertices have even degree. So this graph is basically non-Eulerian. Okay, now the third solution, what the third solution is saying, this is your graph G, remember? Okay, so the third solution is saying that you create a new copy G dash of G. Okay, so G is already there. Okay, notice G is already there like this. G is already there. And what you do, you create a copy. You create a copy of G. This copy you are creating. Okay, basically, you can see this G dash copy you are creating. This is G. And notice what this question is saying, that create a new copy G dash of graph G and add an edge. We need to add edges connecting each pair of corresponding vertices. Okay, we need to add edges like this, that okay, between D comma D, between A comma A, between B comma B, okay, and between C comma C. Is this clear? Between C comma C. I hope you understood this point. So you can see that we have this G we have and this G dash we have. Okay, so now this is H. Overall, remember, this is your new graph H. So tell me, is this new graph H Eulerian? Let me know, is this new graph H Eulerian? No, this is not Eulerian, because notice here the degree is now 3. For this vertex D, the degree is now 3. For this vertex C, the degree is now 3. Here the degree is now 4. Here the degree is 4. Here the degree is 2. Here the degree is 2. Okay, but notice one thing, that not all vertices have even degree. Okay, you can see that this vertex has odd degree. Okay, so definitely I can say that this H here, this H is also non-Eulerian. So this third solution will not guarantee that you will get a Eulerian graph. Okay, the third solution will not always give you a Eulerian graph. Actually, what is the problem in the third solution? Let me know. In the third solution, where is the problem? The problem is that, notice. The problem is that all the previous even degree vertices will become odd degree vertices. Yes or no? Notice one thing. In this third solution, the problem is this, that for every vertex, degree is increasing by 1. Yes or no? This is the problem. For every vertex, degree is degree is increasing by 1. Okay, yes or no? Degree is increasing by 1. This is the problem. Notice. For every vertex, degree is increasing by 1. So all the previous odd degree vertices, they will become new even degree vertices. Yes or no? And all the previous even degree vertices, they will become odd degree vertices. And that is the problem. Do you agree with me? Did you see the problem in this solution 3? In the solution 3, you can notice we are making the corresponding vertices adjacent. Okay, between the corresponding vertices, we are adding an edge. Okay, this edge we are adding between corresponding vertices. So what is happening? For every vertex, the degree is increasing by 1. So all the previous odd degree vertices, they will become even degree vertices. All the previous even degree vertices, they will become odd degree vertices. That is the problem. You can see this B comma C, they were previous even degree vertices. Now in this H, in the new graph, they have become odd degree vertices. So this is the problem. Can you give me a solution? Tell me, can you give me a better solution instead of 3? Of course, this statement 3, this will not work. This first is not working, the third is not working, the second is working. But can you give me a solution, like a better solution, which will guarantee that I will get a Eulerian graph? Okay, create this, consider this variation of C. Okay, consider this variation of C, that what you do, this G, you convert, okay, to G dash, two copies you create. Okay, is this clear? In this G dash, this is basically copy of G. And then what you do? Then you connect corresponding odd degree vertices. Okay, yes or no? Connect, connect, connect only corresponding odd degree vertices. Okay. See, notice one thing, that this G, this was already non-Eulerian. This was already non-Eulerian, simple connected. Okay. So now tell me, will this solution work? Again, I'm asking, will this solution work or not? Is there any problem in this solution? Can you find some problem in this solution? This variation is not there in the question. A new variation I am giving you. In this question, the variation is not there. This variation that I am discussing, this new variation that I am discussing, this is not there in this given question. Now you tell me, will this solution, will this variation work? I am saying that this graph G, what you do? You make a copy of G, okay, this G dash, this is copy of G, and you connect only corresponding odd degree vertices by an edge. Okay, so tell me, will it work? Tell me one thing, tell me one thing. The Eulerian graph, that must be connected also. Okay, just consider this situation. If I have this type of graph, let's assume G is like this. G is like this is G. Okay, and here you can see there is no odd degree vertex. So if I apply this variation, if I apply this variation of third, okay, if I apply this variation of C, or I can say third. So tell me, if I apply this variation of third, then what I will get? I will get this A, B, C, D. This is G, and I will make a copy A, B, C, D. Okay, this copy I will make. And what I will do? You can see in this variation of third, you can notice I am saying that you make a copy of G and then you connect only corresponding odd degree vertices. Okay, here you can see that we don't have any odd degree vertices. So this new graph that you got, this is not connected. This is not connected. So this new graph that you got, this is non-Eulerian. This new graph that you got, this is non-Eulerian. Okay, so can I say this variation will work or not? Very simple question I'm asking, that this variation of third, it will work or not? Because remember, this new graph that you got, this is not connected. So this graph is non-Eulerian. This graph is not Eulerian. Okay, so tell me one thing. This variation is working or not? If you are thinking this variation is not working, then please notice one thing, that in the original graph we don't have any odd degree vertex. This original graph that I have taken, this is already Eulerian. But actually in this question, if you look at this question, the original graph is non-Eulerian. So means the original graph will have at least two vertices of odd degree. Yes or no? So notice one thing. Notice one thing, that this is not a counterexample of variation of third. Okay, means remember this is already Eulerian. This is already Eulerian. So actually the way this variation will actually work. This is what I'm saying, that this variation will always work. Will always work if input graph is non-Eulerian, is connected and non-Eulerian. Okay, is this clear? Please tell me, did you understand? This is a very nice, beautiful variation that we have created. This variation is not there in the options. Okay, in the AIMT one, I did not give this variation. Okay, but did you understand this variation of third? This variation of third will actually always work. It will always work if the input graph is connected and non-Eulerian. And because our input graph is actually connected and non-Eulerian, so definitely actually this variation will work. Okay, because here you are making the corresponding odd degree vertices, you are making them adjacent. So for all the odd degree vertices, the degree will increase by 1. So all the previous odd degree vertices will become even degree vertices. All the previous even degree vertices, they will be as it is, nothing change. Yes or no? So basically in this new graph, all the vertices have even degree. Okay, is this clear? Let me know. So remember, in this graph H, you have all even degree vertices. All even degree vertices. And of course, this is connected also because the old graph was connected. Okay, this old graph was connected. Okay, this new graph, this is also connected. And in the old graph, because this was non-Eulerian, so we have at least two odd degree vertices we already have here. Yes or no? At least two odd degree vertices we have already have here. Greater than equal to two odd degree vertices in G. Okay. I hope you understood. Okay. So finally I can say that this third solution, this will actually not work, and we have seen variation of third which will work. Okay, now let's see the next. The next is saying duplicate all the edges of G. If we do this, if we duplicate all the edges of G, then the new graph that we will get, that will not be a simple graph, but that's fine. The graph, the Eulerian graph that I want to construct, that that may not be simple. Already we are saying that the new Eulerian graph that we want to construct, that may not be simple, not necessarily simple. Okay, so here please understand that this C, this fourth solution. Okay, look at this fourth solution. Duplicate all the edges of G. If you duplicate all the edges of G, for example, consider a graph like this A, B, C, D. This graph you have. Okay, this is your graph G. Now you tell me, if I duplicate all the edges, the fourth solution, if I apply, then what I will get? The fourth solution, if I apply, then what I will get? Then let's duplicate all the edges. Okay, means like this. Duplicate all the edges. So like this, like this, like this. Multi edges. Yes or no? Multi edges, parallel edges we are getting. So of course this graph is non-simple. But the point is the degree, look at the degree of any vertex. We are duplicating every edge of G. Every edge of G we are duplicating. Now you tell me, what about the degree of every vertex? Now the degree of every vertex will become even. Yes or no? You can notice now the degree here is 2. Okay, what is the degree here? That is 6. Okay, the old degree was actually 3, and here the degree was 1, here the degree was 2, here the degree was 2. Now notice, because we are duplicating every edge, every edge we are duplicating, so degree is doubling. Yes or no? Degree 4, degree 4. So basically in this new graph H, in this new graph H, look at the degree of any vertex V, that will be twice the degree of V in G. Okay, the degree of V in H, that is twice the degree of V in G. Is this clear? Please tell me. Let me know. This beautiful point, very simple point. I am saying that because we are doubling, we are duplicating every edge we are duplicating, every edge we are duplicating. So the degree of every vertex will double, and you already know that 2 into even, that is also even, and you also know that 2 into odd, that is also even. When you double any integer, then it will become even. So in this new graph, every vertex has even degree. Yes or no? Each vertex even degree. And because the old graph was connected, so the new graph is also connected. This graph G, this was connected, so the new graph is also connected. And in this new graph, every vertex has even degree. So this new graph, even though it is non-simple, it is not simple. This H is not simple because we have parallel edges, but this is Eulerian. Yes or no? This H is not simple. But the point is that this is Eulerian. Okay, yes or no? This is what the question is asking. So yes, this will work. So far these two are working. What about the last one, the fifth solution? Add edges to G until it becomes a complete graph on V vertices. So tell me, if you have a complete graph on V vertices, then is it guaranteed that it will be a Eulerian graph? No, it is not guaranteed. You can easily see, even if you make complete graph. For example, look at this K4. Look at this K4. Okay, look at this K4. In this K4, every vertex has what degree? Every vertex has degree 3, 3, 3. Every vertex has odd degree. So this K4 itself is non-Eulerian. So how it can help you? See, you are thinking that your input graph is non-Eulerian, and you are thinking that, okay, let's convert this to complete graph. Let's add edges. Okay, you will be adding edges to create a complete graph, and you are thinking that complete graph will help you. You are thinking that complete graph will be Eulerian, but that's not necessary. The complete graph may or may not be Eulerian. This K4, this is non-Eulerian. So definitely this solution fifth, this may not help you. Yes or no? Okay, is this clear? Let me know. So you can see that this fifth solution, let's talk about it. Okay, consider this graph G on 4 vertices. Let me give you a graph G: A, B, C, D. Okay, consider this graph G. You can clearly see that this graph G, this is non-Eulerian. Okay, even if you what you do, you apply the fifth solution and you convert this graph by adding edges. You keep adding edges and you make it complete graph. Okay, let's make it complete graph like this. Let's make it complete graph like this. Now also what you can see? You can see that here also the degree of every vertex is actually odd. Okay, so this is also non-Eulerian. Okay, that's it. I hope you understood. So finally, for this question, what is the answer? The question is asking which of the above processes will always correctly construct graph G, graph H. Okay, Eulerian graph H. So you can see that the answer will be second comma fourth. Okay. Also, we have seen variation of third. Also, we have seen variation of third. That also we have seen. The variation of third also we have seen. Okay. This That's it. I hope you understood the solution. The complete analysis of this question. Did you understand? Don't worry if you did not solve it in the AIMT. Don't worry. Okay, this was in the hard category. Okay, we have already marked it as hard. You can see. Okay, you can check the marking. We have already categorized this as a hard category. Okay, this was not an easy question, I can tell you, because I'm explaining, so it is taking time. But actually, if you solve it, then you will see that it will not take time. Okay, this question is actually not time consuming. Okay, in the gate exam, if you solve it by yourself, then it will not take time, because I'm explaining and I'm doing the complete analysis I'm doing. So that is the reason this is taking time. Did you love this question? Let me know. What do you think? Yes, this question was lengthy. Yes, this question was hard. That is the reason I'm saying that you don't have to worry about this question. Take this question for learning. In the gate exam, not every question is to solve. In the gate exam, there are some questions which are meant to be skipped. In the gate exam, there will be some lengthy question, there will be some hard question. Okay, and those questions, if you skip, you can save a lot of time, and in that time, you can solve some other questions, some easy questions, some moderate questions you can solve. Please understand this thing, that in the gate exam, not every question is meant to be solved. You must know, you must choose your questions. Okay, you must choose your enemies wisely, something like that. You must choose the questions that, okay, this is the question for me, I will solve it. This is lengthy question. Okay, if I solve it, it will take 10 minutes, 15 minutes. Okay, let me skip it. Maybe I will come back to it at the end. Maybe at the end of the gate exam, if I have enough time, some extra time I have, then I will solve it. Okay, but at the end also, if you don't have extra time, then also don't worry. The hard question, the lengthy question, you can skip. You can save a lot of time. You can give that time to other questions, and you can maximize your scores. Okay, you can maximize your marks. Remember, the gate exam is just like your knapsack problem, 0 1 knapsack problem. Okay, in the 0 1 knapsack problem, what happens? Tell me. In the 0 1 knapsack problem, you may have seen this type of situation, that in the 0 1 knapsack problem, this type of situation you may have seen, that if some item will give you a lot of value, but the value divided by the weight, okay, the value divided by the cost, I can say, it this item will give you a lot of value, but the cost is also a lot. Okay, then in that case, it is not beneficial. Maybe you can take some other items, you can take where the value divided by cost, I can say, that is high. Here the value divided by cost, maybe that is low. Okay, so you don't take it and you take the remaining. In the 0 1 knapsack, you may have seen this type of situation. Yes or no? Okay, so the same situation happens in the gate exam also. Okay, in the gate exam also, the same situation happens in the gate exam also. Remember, there are some questions. Let's assume there is a 2 mark question. Okay, and let's assume this 2 mark question will take, let's assume, 10 to 15 minutes. Okay, and there are, let's assume, 4 or 5 1 mark questions, 4 or 5 1 mark questions, which will take total, let's assume, 10 minutes. Then According to 01 knapsack problem, if you want to maximize your benefit, if you want to maximize your marks in the gate exam, then what you should do? This is what you should do. Yes or no? I hope you understood my point. So in the gate exam, some questions are meant to be skipped. There are some questions, if you skip them, then you can maximize your marks. Okay, I hope you understood this. Let's solve the next question. Let's solve this question from the cache memory on a computer with 32-bit memory address. The length of memory location is 1 byte. What it means? The length of memory location is 1 byte. That means we have byte addressable main memory. Yes or no? Okay, you can see the length of memory location, that is 1 byte. So basically, this simply means that we have byte addressable main memory. At every address, we have 1 byte. And I can say that in the main memory, every byte has an address. Okay, so you can see byte addressable main memory. Very simple. Now, you can see the memory address, that is 32-bit. So here on this computer, we have installed set associative cache. We have a set associative cache also on our system. The cache memory size, that is 16 KB. The block or line size, that is 16 bytes. The set associative cache is 4-way. Into which set in decimal? In which set in decimal is mapped the content of memory address? The content of this memory address will map to which set? Okay, this is what the question is asking. Okay, so let's write all the data that we have. First of all, the address size, the main memory address size, that is basically 32 bits. Next, byte addressable main memory, but that is by default. Okay, yes or no? By default, if this line is not given, then also by default the main memory is byte addressable. Every byte has an address, or I can say on every address you will find 1 byte. Okay, yes or no? So very simple. And we have 4-way set associative cache. Okay, the cache is basically 4-way set associative cache. This is what we have. Next, the cache memory size 16 KB. The size of cache, that is 16 KB. Tell me one thing. In this size of cache, do we include the tag directory also? You already know that in the cache memory, we have two parts. One is tag array and another is data array. Yes or no? In the cache memory, there are two parts: data array, tag array. Tag array is also called tag directory. So when I say size of cache memory is 16 KB, then do we include both the data array and also the tag array? Basically, the total size are we talking about? No, we are not talking about the total size. Remember, when we say size of cache memory, then basically we are only considering the data array. We are not considering the tag array. The cache memory has two two physical part. Okay, there is a physical part which is called tag array. There is a physical part which is called data array. But this size of cache memory, that is basically only size of data array. Okay, so here now you can see this is 16 KB. And what the question is saying next? The block size 16 bytes. 16 bytes. Next, that's it. Okay, so here we have set associative cache. So first, let's find the address division. Okay, you can see for address division in the set associative cache, the main memory address, the physical address, you can divide into three parts. What are the three parts? The three parts are tag, index, and block offset. Offset, yes or no? So remember, this offset, this is byte offset or block offset. You can call it offset, or you can call it block offset, or you can call it byte offset. Okay, and what about this index? In the set associative cache, this index, this is basically set index. In the direct mapped cache, the index is line index. Yes or no? In the direct mapped cache, the index is line index. And in the set associative cache, the index is set index. And these remaining bits, you can see that is tag. Okay, so that's it. Very simple. I hope you understood. Now, Let's see here. Tell me, what is the size of block offset? Means how many bits for block offset? So that you can find from the block size. The block size is 16 bytes. It means in one block there are total 16 bytes. So if I want to address a particular byte within a block, in this block there are 16 bytes. Within this block, if I want to address a particular byte, then how many bits I need? That will be 4 bits. Yes or no? So very simple, that from here I can say that 4 bits are required for offset. 4 bits for block offset. Okay, so here I can say 4 bits. Okay, what about this set index? So for this set index, how many bits required for set index? We need to find the number of set. Okay, so let's find the number of set. First, you find the number of lines. In the cache memory, how many lines will be there? In the cache memory, what will be the number of lines? So you can see that number of lines, that will be equal to this cache memory size divided by line size. Because remember, the size of cache memory, this is basically number of lines multiplied by line size. So number of lines, that is size of cache memory 16 kb divided by the line size, that is 16 bytes. Okay, so this will be 2 power 10. These many lines are there. And what will be the number of set? What will be the number of set? So you can see that in one set we have 4 lines. Okay, the set associative cache memory, this is 4-way set associative. So in one set we have 4 lines. So how many set will be there? That will be number of lines divided by the associativity. The associativity, that is 4-way. Okay, in one set we have 4 lines. So finally here you can see 2 power 10 divided by 2 power 2, that will be 2 power 8. These many set. So you can see we have 2 power 8 set. So for set index we need 8 bits. Okay, and remember this total, the address size, that is 32 bits. This is 32 bits. So for tag, how many bits we need for this tag? That will be 32 minus 8 minus 4. 32 minus 8, that is 24. 24 minus 4, that is 20. So basically 20 bits we need for tag. Okay, now what the question is asking? Now we have the address division, the physical address division. So let's see, the question is asking that this memory address we have, the content of this memory address will map to which set? Okay, this is what the question is asking. So you can see that this given memory address, the given memory address of a byte. Okay, so this is a memory address, that is 10FFCFF. Okay, in the hexadecimal, this address is given in the hexadecimal. Okay, you can notice one thing, how many hexadecimal digits we have here. So that is basically 7. Okay, 7 hexadecimal digits we have. If you convert this to binary, if you convert this to binary, then what you will do? Every hexadecimal digit you will replace by the corresponding 4-bit binary number. Every hexadecimal digit that corresponds to 4-bit binary number. Yes or no? So you can see that here we have total 7 hexadecimal digits, 7 multiplied by 4, these many bits, and that is basically 28 bits. Notice this is actually 28 bits, but in the address, how many bits we have? In the address, how many bits we have? Tell me. You can notice that here you have basically 28 bits. But remember, this is a memory address. So the memory address must have how many bits? Total 32 bits it must have. Okay, so what it simply means? Then what is the reason that this address has only 28 bits? The reason is very simple, because this will be 0. Yes or no? Okay, this will be 0. I hope you understood. Now you can see that 8 multiplied by 4. Okay, now you can see it will be 32 bits. Anyway, so the point is that this address that is given to us, this is basically a main memory address, and the main memory address size, that is 32 bits. Okay, let's convert this. What we need, we just need the set number. Okay, means this memory address will map to which set? Okay, we just need the set number. So remember one thing, already we know that in the address, in the memory address, the least significant 4 bits, that is your block offset. Yes or no? Okay, notice that here we have this address 10FFCFF. Okay, you can see these are the 4 bits. Okay, these are 4 bits. So the least significant 4 bits, that is basically your block offset. This we have already seen that in the main memory address, this is the main memory address division. in the main memory address, the least significant 4 bits, that is for block offset. Then the next 8 bits, that is your set index. Okay, the next 8 bits, this is your set index. Please understand that this next 8 bits, this is your set index. This is your set index. Okay, so from this set index, we can easily find, we can just convert this to decimal. This is what the question is asking, that to which set it will map in the decimal. The set number we need to find in the decimal. So basically, we have, this will be the set number, I can say. The set number to which this address will map, that is basically CF. Okay, in the hexadecimal. Now you can convert this to decimal. How to convert this to decimal? To convert this to decimal, what you will do? Very simple. C multiplied by 16 power 1 plus F. Okay, yes or no? So this is how you can convert this to decimal. C means what? F means 15 and C means 13, right? So C C means 12. Okay, so it will be basically 12 multiplied by 16 plus 15. You can calculate the value. Okay, you can calculate the value. So what that will be? Can anyone tell me? This value you can calculate. 12 multiplied by 16 plus 15. Okay, I think that will be 207. Okay, let me just calculate this value. Yes, 207, that is correct. Okay, so basically, I can say that this given main memory address, we can simply say that this into which set it will map, into which set it will map in decimal. So that answer we got set number 207. Okay, that is the answer. I hope you understood the complete analysis of this question. So this was a simple question, right? In which category you will put this question? Did you do this correct? Anyone here who did not do this correct? Did you make any silly mistake? This was a simple standard question from the cache memory. This was easy question. If you have studied the cache memory, then this is a easy question. Okay, let's move on now. Let's solve this digital logic question. This is actually a very simple question, but still many students made mistake in this question. The question is asking, according to De Morgan's theorem, the complement of x or y and z, what will be that? What many students have done? What they have done? See, to apply the De Morgan theorem, we want to find the complement of x or y and z. We want to find the complement of this. So you can apply the De Morgan theorem. What some students have done, let me tell you. They have blindly done this, that okay, you already know the trick, that when we apply the De Morgan theorem to find the complement of any Boolean expression, you have a Boolean expression, to find the complement of any Boolean expression, you can apply the De Morgan theorem. And basically what you can do, if your expression contains only these operators and or complement, okay, and or negation, basically also variables are there, the complement of variables are there, 0 comma 1 might be there. Basically, if you have these things in your expression and if you want to find the complement of your expression, then what you can do, then you already know that this plus we will convert to and, or will be, or will become and will become or, and all the literals they will complement, yes or no? All the variables, all the literals basically they will complement. So it will be x bar, y bar, z bar. Okay, and this is what many students have done, and finally they have done okay, that option B, this option B. But actually this is wrong. What is wrong here? In Go classes lectures also I told you this point, that you should take care. Don't be blind. When you have a easy question, then don't be blind. Okay, here notice one thing. We have this expression x or yz. First you understand this expression, that you have, that is basically x or yz. Please notice that and has more priority than or. So actually this expression is actually x or y and z. This expression is not x or y and z. Okay, so and has more priority than or. So this is your expression. Now you can find E complement. Yes or no? What will be E complement? Your X or Y and Z. Now you can find its complement. Now you can do your trick. Now you can apply the trick, or I can say the De Morgan law you can apply. So this X will become X bar, this or will become and inside, this Y will become Y bar, this Z will become Z bar, this and will become or. This will be your final answer. Okay, so the final answer will be option C. This was a easy question in which many students have made mistake. Again, I am telling you that in the easy questions, don't become too excited. Okay, I've seen many students when they see a very easy question, very trivial type question, they become very casual immediately. Okay, they become very casual, they become, I can say, too excited, and they make mistake. Notice one thing: if you have a easy question, then make sure that you don't wrong it. Okay, you don't make mistake in it. Okay, yes or no? So basically, read the question very carefully. If this is a easy question, then read the question carefully and solve it. Okay, don't become blind. This is what I'm saying. Okay, many students have made mistake here. Is there anyone here who made mistake here in this question? Anyone made mistake? So this was a easy question, but silly mistakes are possible. Don't worry, it's good thing that you made mistake in the go classes AIMT. Okay, make all the mistakes in our test series, in our mock test, in our AIMT. Make all the mistakes, and we will make sure that you make all the mistakes. We will keep putting this type of questions from which you can learn something new. Okay, yes or no? The concept you already know, I have no doubt. The concept you know, but just learn this type of small things also you learn. These are also part of preparation. Okay, so we will make sure that you make all your mistakes in our AIMTs. Okay, 4 more AIMTs are coming. This was just all India mock test 1. Then you have all India mock test 2, 3, 4, 5, then maybe 6. Okay, the point is that just make all the mistakes that are possible, and in the gate exam you do correct. Okay, yes or no? Get low marks in our AIMT, that is fine, but get top rank in the gate exam. And this has happened many times. Many students, what they do, many students, they make mistakes in our test, and then in the gate exam the same question comes and they don't make mistake. Then after the gate exam they tell us that, sir, this question came as it is from our test series, from the goclasses test series. This question is based on goclasses test series, and I made it wrong when I attempted the goclasses test. I made it wrong, but in the gate exam I did it correct. So that is the purpose. Overall, the purpose is to top the gate exam. Let's solve this question. This is a beautiful question from theory of computation. Non-deterministic finite automaton is given to us, and the question is asking, let P be the probability that a uniformly random string from ABC power 5 is accepted by the above automaton. What is this probability? The question is asking for probability. Some options are given to you. You can see 32 by 243. Basically, the denominator, that is 243. That basically means 3 power 5. Okay, but the numerator, that is different. Okay, the question is asking for probability. Okay, see, focus on this question. The question has given us a non-deterministic finite automaton, and the question is asking that what is the probability that from this set ABC power 5, these are the 5 length strings. So the question is saying that from this set of 5 length strings, this is the set of all the 5 length strings. From this set, if I take a random string uniformly, okay, I can take basically taking any string, whatever string you take, okay, that basically has equal probability. Okay, like all the strings, this is a set of 5 length strings, and in this set, which string you are taking, that has equal probability. A uniformly, you can see, uniformly random string we are taking from this set, then what is the probability that that string will be accepted by this automaton? Okay, and this is a very easy question. What you need to do, you just need to see how many 5 length strings are accepted by this automaton. Okay, agree? Notice one thing. Look at this set. This set has 5 length strings. All the 5 length strings. This does not have 0 length string. This does not have 1 length string. This does not have 2 length, 3 length, 6 length, 4 length. This has all and only 5 length strings. These are all and only 5 length strings. So how many strings are there in this set? Tell me. In this set, how many strings are there? You can see we have 5 length strings, right? We have 5 length strings. Okay, and remember our alphabet, that is ABC. So here I can put A or B or C. Here we have three choices. Here we have three choices, three choices, three choices, three choices. Yes or no? Do you agree? For every position, we have three choices. We can put here A or B or C, here A or B or C, and so on. So how many 5 length strings are there? That will be 3 power 5. Okay, yes or no? Now, out of these 3 power 5 strings, one string we are taking uniformly, one string we are taking. Okay, out of these 3 power 5 strings, what you are doing? You are taking one string uniformly. Okay, W, take take a string, okay, uniformly. So basically what to do? Let's call it W. Okay, you can see, take one string, take one string uniformly. Means whatever string, any string you can take. Okay, so you can see we are taking one string, that is W. Now the question is asking what is the probability that this W will be accepted by this automaton. And basically the question is asking that the probability that W belongs to the language of this automaton. Let's call it automaton M. Okay, so you can see the probability that W belongs to LM. This is what the question is asking. Is this clear? Did you understand the question? What the question is asking? The question is asking that the probability that this W belongs to the language of this automaton. Okay, so let's see. Tell me how many 5 length strings are accepted by this automaton? Simple question I'm asking. By this non-deterministic finite automata, how many 5 length strings are accepted? Okay, so just tell me how many 5 length strings, because we only care about the 5 length strings. We do not care about the 0 length string. We do not care about the 1 length string. We only care about the 5 length string because we are picking one 5 length string. Okay, and for that string we want to check what is the probability that that string will be accepted. So we are only interested in the 5 length strings. How many 5 length strings accepted? How many 5 length strings accepted by this automaton M? Okay, so let's find that. You can see, notice this is a beautiful automaton. What we are doing from the start state, without reading any symbol you can either go to this final state, or without reading any symbol you can go to this final state, or without reading any symbol you can go to this final state. let's call it let's call it state PQR. Okay, or maybe you can call it like state XYZ, state XYZ. So you notice one thing, that in this state X, which strings we are accepting? In this state X, just tell me what are the language of X. Means in this state, which strings we are accepting? Without reading any symbol we are going to X. Okay, and in this X, in this state X, A comma B can come. There is a loop on A comma B, but the C cannot come. Basically, what is LX? LX is basically A or B whole star. And similarly you can see what is LY. You can see without reading any symbol you are going to state Y. In this state Y, there is a self loop on A comma C. Means all the strings of A comma C will be accepted which do not contain B. Okay, yes or no? In this state Y, all the strings of A comma C will be accepted which do not contain Y, which do not contain B. In this state Y, all the strings of A comma C will be accepted which do not contain B. Okay, so that will be basically A or C whole star. What about L of Z? What strings are accepted by the state Z? So you can see that in this state Z, without reading any symbol, you are going to state Z. In the state Z, your B comma C self loop. It means that all the strings of B comma C will be accepted which do not contain A. So basically, B or C whole star. Okay, and we need to find how many 5 length strings. So what I need to do, notice I can see how many 5 length strings will be accepted here, how many 5 length strings will be accepted here, how many 5 length strings will be accepted here. Yes or no? Okay, so this is what I can do, that I already know that this Lx, this is A or B whole star. Okay, this Ly, this was A or C whole star. And this Lz, this was B or C whole star. Okay, tell me how many five length strings are here? How many number of five length strings? Number of five length strings. How many five length strings are in this set? Means by the state X, how many five length strings will be accepted by the state X? So very simple, that will be 2 power 5. Yes or no? Okay, why 2 power 5? Five length strings. So you can see five length strings. And here you can see that here you can either put A or B. Here you can either put A or B. Here you can either put A or B. Yes or no? So the point is very simple, that here you can put A or B. Here you can put A or B. Okay, so the point is that how many five length strings are accepted by the state X? That will be 2 power 5. Similarly, here also the same thing. Okay, so you can see that similarly here also you can see 2 power 5, 2 power 5. Yes or no? You can see 2 power 5, 2 power 5. These many five length strings accepted. These many five length strings accepted. Okay, so tell me total, by this automaton, total how many five length strings will be accepted? So can I say that will be 2 power 5 plus 2 power 5 plus 2 power 5? Can I say that? Can I say that total number of five length strings accepted? Total number of five length strings accepted. Total number of five length strings accepted by M. Can I say that will be 2 power 5 plus 2 power 5 plus 2 power 5? Can I say that? Notice one thing. Here you are applying the sum rule. Yes or no? Here you are applying the sum rule. But whenever you apply the sum rule, you are applying the sum rule. But whenever you apply the sum rule, you must check, are they disjoint or not? Are they mutually disjoint or not? Or do they have something common? Did you count the same string many times or not? So tell me, which strings you have counted many times? Notice one thing. Here also you have A power 5, here also A power 5, here also B power 5, here also B power 5, here also C power 5, here also C power 5. So did you notice that these strings A power 5, B power 5, C power 5, these strings you have counted two times? Yes or no? Is this point clear? So very simple point. This is what I am saying, that you can see A power 5 is accepted here also, A power 5 is accepted here also, and A power 5 is accepted here also. Notice B power 5, that is accepted here also, and that is accepted here also. And notice C power 5, that is accepted here also, and that is accepted here also. Okay, yes or no? So A power 5, B power 5, C power 5, these strings you have counted double time. And tell me one more thing. We are only finding the five length strings. We are only interested in the five length strings. You tell me, among the other five length strings, what about the other five length strings? Did we count them only one time? I'm asking, what about the other five length strings? Did we count them only one time? Yes, we counted them only one time, because notice one thing. Except these five length strings, whatever five length string you take, for example, let's take A power 4b. If your string contains both A comma B, then that will not be accepted in these states. If your string contains both A comma C, then it will not be accepted in these states. If your string contains both B comma C, then your string will not be accepted by these states. So notice one thing, that only these strings you have counted double time. All the remaining strings you counted only once. Because if your string contains A comma B, then that will not be accepted by these two states. If your string contains A comma C, that will not be accepted by these states. So overall, I hope you understood the point, that only these three strings you have counted double times, and we want to count them only one time. So what I need to do? I need to do minus. Okay, yes or no? Inclusion exclusion principle, or basically you can say subtraction rule, or inclusion exclusion principle. So overall, basically, this you should take care, that you need to do this. Okay, why this 3? Why we are putting this 3 minus 3? This is for a power 5, b power 5, c power 5. So finally your answer will be what? That will be 3 into 2 power 5 minus 3. Okay, now you can easily find the probability. So the probability that we need to find, that will be, so you can see that these many 5 length strings are accepted by M. Okay, by this machine M, we can see that these many 3 into 2 power 5, you can see that 3 into 2 power 5 minus 3, these many these many 5 length strings are accepted by M, and total 5 length strings that we have, that is 3 power 5. Okay, you can calculate this, and I think it will be 93 divided by 243. I think this will be the answer. Okay, so I have seen many students, they made mistake that they did not do this minus 3. Did you make the same mistake? Tell me. In this question, did you make the same silly mistake? How many of you, just tell me honestly, how many of you forgot about this minus 3? You did not do this minus 3. So here I have a note for you. I have a note for you that whenever you apply the sum rule, whenever you want to add, okay, whenever you apply the sum rule, immediately make sure, immediately make sure mutually disjoint. Make sure mutually disjoint. Okay, is this clear? Make sure mutually disjoint sets. I hope you understood this point. Very simple point. So this question was not hard. This question was not hard, remember. This was a easy to moderate question. What do you think? Was it hard? In which category you will put it? Will you put it in the easy category, moderate category, hard category? This type of question has not come in the GATE exam so far, I think, where automaton is given to you and they are asking the probability that a string will be accepted or not, yes or no. This type of question where automaton is given to you, automaton is given to you, and the question is asking that what is the probability that some string will be accepted or not, probability that some uniformly taken string from a set, okay, this w you are taking from a set, from this set you are taking this w, okay, and then you can see that what is the probability that this w will be accepted by this m or not. Okay, what are the variations possible? Can anyone tell me? Just tell me a simple thing. What are the variations possible? What are the variations possible here? Instead of this machine, instead of this automaton, they can give you regular expression. Yes or no? They can give you regular expression. They can give you DFA, they can give you NFA. Maybe they can give you some push down automaton. Okay, basically some variations are possible. Maybe they can give you a grammar. Okay, yes or no? So these are the variations that are possible. In this question, of course, many variations are possible. Okay, I can give you a grammar also, and the same question I can ask you. I can give you regular expression, same question I can ask you. Basically, like that, variations are possible. I hope you understood. Let's solve this question from theory of computation. And this is a beautiful question based on ambiguity of grammars. Let's read the question. The following grammar is ambiguous. You don't have to check it. This is given to you that this following grammar is ambiguous. Can anyone tell me why this grammar is ambiguous? We already know that any context free grammar is ambiguous if and only if there is at least one string which has more than one parse tree. Yes or no? So here actually you can notice that consider this string BC. Consider this string BB. Okay, consider this string BB. This string you consider, or maybe you can consider this B string you consider. Okay, then for this B string, what you can do? You can do like this BBC. This B can go to epsilon, this C can go to epsilon. Okay, double B, double B. Actually, before for this single B, you have only one parse tree. For single B, okay, for this string single B, you have one parse tree, but for this string there will be more than one parse tree. Okay, for this double B, what you can do? You can do like this BBC. then this b can go to, and this can go to epsilon. This pass tree you can get. Okay, and you can see another pass tree I can get, that is like this: a can go to b, capital C. Here this b can go to epsilon, this can go to b. So like this, I hope you understood. So definitely yes, this grammar is ambiguous. You don't have to check, this is given to you that this grammar is ambiguous. But what the question is asking, the question is asking to demonstrate, to prove this ambiguity, we can use pairs of derivations. To prove that this grammar is ambiguous, we can use pairs of derivations. Here are four different pairs. Okay, four options are given to us. You can see these are the four options. In every option we have pair of derivation. Okay, now you can see for each pair of derivations, select it. You need to select it if the pair correctly proves that the grammar is ambiguous. Do not select it if the pair does not give a correct proof. If the pair does not give a correct proof, then don't select it. Which of the following pairs of derivations correctly prove that the grammar is ambiguous? Okay, so to solve this question, what is the concept actually? What is the concept behind this question? Let me tell you the concept. The concept is this: you already know that when can I say a context free grammar G is ambiguous? A context free grammar G is ambiguous if there is at least one string which has more than one pass tree. But remember one thing: in any context free grammar G, for any string, the number of rightmost derivation will be equal to the number of leftmost derivation will be equal to the number of pass tree. Okay, see some concepts I am telling you. You can take whatever, context free grammar G you take, whatever. Okay, any context free grammar G you take, and take any, for any string W, for any string W. Okay, for any string W in L comma G, in L of G. Okay, so remember one thing: whatever context free grammar you take, for any string W in the language of this grammar, remember the number of pass tree for W. How many pass trees will be there for W? The number of pass trees for W, that is equal to the number of rightmost derivations for W. Okay, the number of rightmost derivations for W, and that is equal to the number of leftmost derivations for W. Is this clear? This this is true for every string. Whatever context free grammar you take, whatever string you take, this is always true. This is always true. Means for this string W, the number of pass tree will be equal to the number of rightmost derivation, that will be equal to the number of leftmost derivation. So now when you say that a grammar is ambiguous if for at least one string we have more than one pass tree, so the same statement I can also say that a grammar is ambiguous if there is at least one string for which we have more than one rightmost derivation. The same statement I can also say that a grammar is ambiguous if for at least one string we have more than one leftmost derivation. So remember one thing: when can I say a grammar G is ambiguous? You have a context free grammar G. Okay, then remember G is ambiguous. When can I say G is ambiguous? What is the definition? G is ambiguous if and only if. G is ambiguous if and only if there exists a string W. There exists a string W in the language of G. There exists a string W such that such that W has more than one pass tree. More than one pass tree. Okay, is this clear? Very simple. The grammar will be ambiguous if and only if there is at least one string in the language of the G, in the language of the grammar, there is at least one string for which you have more than one pass tree. The same statement I can also, instead of writing more than one pass tree, I can also say more than one leftmost derivation. Okay, more than one leftmost, W has more than one leftmost derivation. Because remember, the number of pass tree will be equal to the number of leftmost derivation. So if you have for this string W, if you have 5 pass tree, then for this string W we have 5 leftmost derivation also. The same statement I can also say that this grammar will be ambiguous if and only if there exists at least one string, there exists such that W has greater than one, more than one rightmost derivation. Okay, is this clear? I hope you understood this. So these are the three definitions for ambiguity. These are the three definitions to say that grammar is ambiguous. Okay, so tell me one thing. If you want to prove that grammar is ambiguous, let's assume this given grammar you have, this given context free grammar G you have. Just tell me, to prove, if you want to give a proof to prove G is ambiguous, to prove G is ambiguous, what you need to do? To prove G is ambiguous, what you need to do? You need to give at least one string and its more than one rightmost derivation. Yes or no? Okay, so remember, to prove G is ambiguous, to prove this G is ambiguous, what you need to do? To prove G is ambiguous, we need to give, we must give at least, we must find at least one string, we must find at least one string W, such that we must find at least one string W and more than one parse tree for W. Yes or no? More than one parse trees for W. Okay, the same thing I can also say, the same thing I can also say that if you want to prove that grammar is ambiguous, then you must give at least one string W and more than one leftmost derivation for W. More than one leftmost derivations for W. The same statement I can also say that, the same statement I can also say that if you want to prove that the grammar is ambiguous, then you must give at least one string and more than one rightmost derivations for W. Is this clear? Very simple. Now let's solve this question. Now let's come back to this question. So here you can see which of the following options will give a correct proof that the grammar is ambiguous. You can notice here we are deriving the same string. For the same string, we have two derivations. Let's see. Both are leftmost derivation, both are rightmost derivation. If both are leftmost derivation, two different leftmost derivation for the same string, then definitely I can say that grammar is ambiguous. If you have two rightmost derivation for the same string, two different rightmost derivation for the same string, then also I can say that yes, grammar is ambiguous. But remember, if you have two different strings, here notice you are giving derivation of two different strings. If you are giving derivations of two different strings, then this is not a proof that the grammar is ambiguous. Yes or no? This does not prove grammar ambiguous. Okay, this doesn't prove grammar ambiguous, because you are giving derivation of different strings, you are deriving different strings. Okay, so this doesn't prove grammar ambiguous. Okay, let's see this first option. In this first option, do we have two leftmost derivation, do we have two rightmost derivation? So you can see this a is going to BBC. Then you can see, then here we only have one non-terminal B, so this B is actually going to B. Sorry, actually we have two non-terminal. Notice we have two non-terminal, capital B, capital C. Here in this sentential form, here we have two non-terminals, and notice what we are doing. This leftmost non-terminal we are replacing, this B we are replacing. So this is actually a leftmost derivation. This is a leftmost derivation for triple B. Okay, you can see A is going to capital B, small b, capital C. Then this leftmost non-terminal we are replacing by capital B, sorry, small b. Then this capital C we are replacing by B. So you can see this is a leftmost derivation for triple B. What about this one? Which type of derivation is this? Is this leftmost derivation, rightmost derivation? Neither, both. Remember, a derivation can be leftmost derivation, a derivation can be rightmost derivation, a derivation can be both, a derivation can be none. Okay, all the four possibilities are there. So let's say this derivation, is it leftmost derivation, is it rightmost derivation, is it both, is it none? So here you can see A is going to capital B, small b, capital C. Then notice one thing, that this C, which is the rightmost non-terminal, here you can see we have two non-terminal. This C is the rightmost non-terminal, this is what we are replacing. So this is actually rightmost derivation of triple B. You are giving one leftmost derivation, you are giving one rightmost derivation, you are giving, is it, does it prove that grammar is ambiguous? This leftmost derivation, this rightmost derivation you are giving, does it prove that grammar is ambiguous? No, this does not prove grammar ambiguous. Okay, is this clear? Very simple. I hope you understood. So I can say that this option A, this is also not a correct proof. Option D, this is also not a correct proof. Let's see option B. Let's focus on option B. In this option B, here we are deriving double B. Okay, so let's see this derivation. A is going to BBC. Then you can see that this B is going to B. So this is actually leftmost derivation of double B. What about this next? What about this derivation? A is going to BBC. You can see A is going to BBC. Then notice this B, this is the leftmost non-terminal. Here in this sentential form, we have more than one non-terminal. Okay, and here you can see that this leftmost non-terminal we are replacing. This B is actually going to epsilon. So this is also leftmost derivation of double B. Both are leftmost derivation of double B. You have two different leftmost derivation of double B. We have two different leftmost derivation of double B. So that is the reason I can say yes. We can say that we can prove. We can say that grammar is ambiguous. This will mean grammar ambiguous. This proves grammar ambiguous. Okay, is this clear? So yes, this is the correct proof, I can say. What about this option C? In the option C, again we are deriving double B. Okay, let's see the first derivation. Is it leftmost derivation, rightmost derivation, both, none? So let's see this option A. Sorry, let's see this first derivation in the option C. A is going to BBC. Then notice this B is going to B. So actually this is actually leftmost derivation of double B. Okay, what about this next? Which type of derivation is this? Is this LMD, RMD, both, none? Okay, so let's see this. B is going to BBC. Next, here notice this C is going to B. So this is actually rightmost derivation. This is rightmost derivation of double B. Okay, so definitely this also does not give you a correct proof. Okay, remember you are giving one leftmost derivation, one rightmost derivation. That does not prove that the grammar is ambiguous. Yes or no? This does not prove that grammar is ambiguous. If you want to prove that the grammar is ambiguous, then for the same string you give more than one leftmost derivation, or for the same string you give more than one rightmost derivation, or for the same string you give more than one parse tree. If you want to prove that grammar is ambiguous, then for the same string you give two different leftmost derivation. Or what you can do, for the same string you give two different rightmost derivation. Or what you can do, for the same string you give two different parse tree. Okay, yes or no? Is this clear? Let me tell you one more thing. Okay, just one example. I have seen many students, they think that, okay, if we have for this W, let's assume we have leftmost derivation. For this W, if we have rightmost derivation, and if they are different, then the grammar is ambiguous. I have seen this. Many students, they have this misconception. See, many students, they have this misconception. Let me share this misconception with you. Many students think that for W, okay, you have a context-free grammar G, okay, and let's assume there exists a W. There exists a W, okay, for at least one string W. Now, if this W has, for this W, let's assume there is LMD and there is RMD, and if they are different, then the grammar is ambiguous. Okay, you can see if W has a leftmost derivation, a rightmost derivation, and both these are different, and both these are different. You can see if W has leftmost derivation, rightmost derivation, and both these are different, then G is ambiguous. Then G is ambiguous. Okay, so let me tell you This is actually nonsense. Okay, I can give you a very easy counter example. Consider this grammar: s going to a b, b, a is going to b, b is going to b. You can easily notice this is unambiguous. Yes or no? This grammar is unambiguous. This is unambiguous. But still, for this string w, for this string w, bb, for this string w, what I can do? I can give you a left mode derivation, a right mode derivation, and both will be different. Okay, for this string w, I can give you left mode derivation, right mode derivation, and both are different. For example, you can see in the left mode derivation, what I will do, s will go to ab, because I'm writing the left mode derivation. So at any point of time, the leftmost non-terminal I will replace. Okay, so you can see this bb and then this bb. Okay, right mode derivation also I can write s will go to ab. Then you can see, because I'm writing right mode derivation, so at any point of time, the rightmost non-terminal I will replace. So I will go to ab, and this finally this bb. Now you can notice that these are actually different. Okay, yes or no? These are different, but it does not mean that your grammar is ambiguous. The grammar is actually unambiguous. You can notice this grammar is unambiguous, but notice that for this string bb, for this string, you can see that we have left mode derivation, we have right mode derivation, and both are actually different. Okay, but it does not mean that the grammar is ambiguous. Is this clear? So again, I'm telling you that the grammar will be ambiguous if there is at least one string for which you have more than one left mode derivation, or more than one right mode derivation, or more than one parse tree. Remember, for any string in any grammar, whatever context free grammar you take, for every string, what will happen? For any string, what will happen? The number of parse tree is equal to the number of left mode derivation is equal to the number of right mode derivation. Okay, is this clear? I hope you understood this question. So, how many of you did this question wrong? I have seen some students, they were saying that in this question these options are correct. Okay, I have seen some students, this is what they were saying, that these options are correct. But actually, if you notice that in this question, only option B is correct. Only option B is the correct proof that the grammar is ambiguous. Okay, option B is the only correct proof among all these options which proves that grammar is ambiguous. So I hope you understood the complete analysis of this question. If you did it wrong in the AIMT, don't worry. You understood this. You understood some new concept. Okay, maybe it will help you in the gate exam. In the gate exam, if similar question comes, then you will not make it wrong. Let me tell you one more thing. This question, as it is, I have taken from the Washington University. Okay, this question, as it is, this question is taken from Washington University. So this is a standard question from a top university. I hope you understood the complete analysis. I hope you loved this question. Let's solve this question from discrete mathematics set theory. For any two set S comma T, we have S, this symmetric difference symbol is there, S symmetric difference T, and this is the definition, S union T minus S intersection T. Yes, this is the definition of symmetric difference. Okay, yes or no? This is the definition of, this is the symmetric difference. This we have, you can notice, the question is saying that we have set S comma T. Okay, and we are defining this operation, this set operation we are defining. Okay, this is called symmetric difference. Let me tell you, also the definition is also given. This is called symmetric difference. Okay, and the question is also saying that this is actually equal to S union T minus S intersection T. Okay, sorry, minus means backslash. Okay, this. So here, first of all, let me tell you that this is actually set difference, means minus. Okay, and you can easily create the Venn diagram to understand what is the symmetric difference. Okay, so let me create the Venn diagram. Here you can see, if this is your set S, if this is your set T, then what we are doing, from S union T, this is S union T. From S union T, we are removing S intersection T. From this S union T, this intersection, this common area we are removing. So which area we will get? We will get this area. This is your symmetric difference. Okay, is this clear? This area, this area, this area, this is your symmetric difference. Okay. I can also say that this symmetric difference, as symmetric difference T, this is equal to S minus T union T minus S. Okay, yes or no? This also I can say, because you can see S minus T, this is the S minus T area. Okay, this area, this is S minus T area, and this area, this is T minus S area. So the union of these two area, that is your symmetric difference. Anyway, so this definition is given in the question. Now the question is saying that let A comma B comma C, these are the set such that A intersection B intersection C, that is equal to phi. Means the common area of all these three set, the common area of all these three set, that is basically empty set. The number of elements in each of A symmetric difference B, B symmetric difference C, C symmetric difference A, the number of elements in each of these, that is equal to 100. Then the number of elements in the union A union B union C. This question you can solve by multiple methods. So let me solve this question by multiple methods, and you tell me which method you loved the most. Okay, so let's see the method number 1. Okay, first let me write the data here. The data is saying that, okay, we have this A symmetric difference B, A symmetric difference C, B symmetric difference A, B symmetric difference C, sorry, B symmetric difference C. Okay, the question is saying that basically their cardinality, number of elements in each of them, that is basically 100. Okay, also what the question is saying, the question is saying that the number of elements in A intersection B intersection C, the common area of all these three set. Okay, so the number of elements there, that is actually 0. And the question is asking A union B union C, what are the cardinality of this number of elements in A union B union C? This is what the question is asking. Okay, so this question you can solve by multiple methods. Let me solve this question first using the Venn diagram. Okay, for this type of question, for any set theory question, you can always think about the Venn diagram. Okay, this is a guideline I am telling you. Okay, rule of thumb, in any set theory question, whenever set are given to you, and if you are thinking how to solve it, then one time you can think about Venn diagram. Okay, maybe it will give you the answer. Very simple. So in most of the set theory questions, you just think about Venn diagram. Okay, maybe that will give you the answer. Okay, so here let's think about the Venn diagram. So let me create the Venn diagram here. You can see this is the A, we have set A, then this is the set B and set C. Okay, so you can see I've created the Venn diagram. Now you just notice one thing in this Venn diagram. What you do, you write the areas. Okay, let me make the full Venn diagram. Okay, so this is the universal set. Like if this is the universal set, this is your U. Okay, so in this Venn diagram, you just mark the areas. Okay, in our Go classes lectures also on the YouTube also I have put the videos, set theory videos you can find, and there I've already told about this area method. What you do, you mark the areas. For example, this outside area, let's call it area, let's call it area 8. Okay, and you can see the remaining areas. For example, you can see, let's call it area 1, area 2, area 3, area 4, only this area, remember, only this area, this area is area 4, area 5, only this area, only this area, only this area, area 5. Okay, this common area of all these set, let's call it area 6, only this area, let's call it 7. Okay, is this clear? And this outer area, let's call it area 8. Very simple. So that's it, areas we have marked. Okay, now can you tell me what is the asymmetric difference B area in this question? Now you quickly tell me, what about asymmetric difference B? Which area are there in this asymmetric difference B? Which areas are there? Asymmetric difference B. So you can see that is your 1427. Yes or no? 1427, these areas. Do you agree with me? Because asymmetric difference B, that means you forget about this common area of A comma B. Forget about common area of A comma B. Basically, from A union B, this is your A union B. From A union B, you remove the common area of A comma B. So you will get A 1427. Okay. What about A symmetry difference C? You can see A symmetry difference C means from the A union C, you remove the common area of A comma C. Okay, the common area of A comma C means 4 comma 6 you remove. So it will be 1537. Okay, what about B symmetric difference C? B symmetric difference C, you can see that is 2534. Yes or no? 2534. That's it. I hope you understood this. Okay, so now, can you notice one thing? This in this you can notice one thing. This one is coming two times. Okay, one is coming two times. Notice. This two is coming two times. Notice something beautiful. Seven is coming two times. Notice. Next, you can see this three is coming two times. This four is coming two times. This five is coming two times. Okay, so what did you notice here? Here you can see that if I do this 100 plus 100 plus 100, then these areas 1, 2, 4, 7, 3, 5, basically these areas I've counted double time. Okay, yes or no? And except which area? You can see except 6,8. Basically, I can say that if I do this, that if I do the addition here, okay, like A symmetry difference B plus A symmetry difference C plus B symmetry difference C, B symmetry difference C. If I do their addition, means that is basically 300. Okay, 100 plus 100, 100 plus 100 plus 100, 300. Now you can see in this 300, notice one thing. Every area except 6 comma A, I have counted two times. Yes or no? Every area except 6 comma 8 counted two times. And 6 comma 8 I did not count. Counted twice. Okay, and remember 6 comma 8 we did not count. Okay, yes or no? Area 6 comma 8 not here. Okay, is this clear? So I hope you understood. And the remaining areas I counted two times. So that's it. Now, if I ask you, can you find the cardinality of union? Means A union B union C. Okay, here basically what is the area? Sorry for that. What is the area of A union B union C? Just give me a second. So, what are the areas in A union B union C? Okay, in the A union B union C, we have area 1, 2, 3, 4. Okay, 5, 7. 5, 6, 7. Yes or no? 5, 7, 6. Okay, is this clear? 1, 2, 3, 4, 5, 7, 6. And notice. This already the size is 0. Okay, already the question is saying that this is your area 6 size. Yes or no? The question is saying that area 6 size, that is 0. This is your area 6. Area 6 size is 0. Okay, we just need to basically find what is the summation of this. So what that will be? That will be 300 divided by 2. Yes or no? That will be 150. I hope you understood. Please tell me, did you understand this? Let me know. Did you understand this? Let me know. So this Venn diagram method, did you like it? See, this is a beautiful method. This Venn diagram method. First, you make the Venn diagram. In any set theory question, if your question has set, then you can think about Venn diagram. Maybe most probably set theory question you can solve using the Venn diagram. So you make the Venn diagram. You label the areas. Once you label the areas, then you can easily solve this question. You can see that in this asymmetric difference B, we have areas 1, 4, 2, 7. In this asymmetric difference C, we have areas 1, 5, 3, 7. In this B symmetric difference C, we have areas 2, 5, 3, 4. You can see that every area we have counted 2 times, every area we have counted twice. And notice one thing, that if I add these, okay, if I add these, means in this 300 we have counted every area 2 times. But the point is that this area 6,8 we did not count. Okay, and remember the area 6 has size 0, and the area 8 anyway I don't want, because I want the size of A union B union C. In the A union B union C, I don't have area 8. I don't care about area 8. Okay, and you can see this area 6, this has size 0, and all the remaining areas I have counted twice in this 300. Okay, so if I want to count them only one time, if I want to find the size of A union B union C, then what I will do? I will just divide by 2 and I will get 150. This is the answer. I hope you understood. Now let me tell you, there is another method to solve this question. Let's see the method number 2. The Venn diagram method is actually very quick method. Okay, but let's see the method number 2 also. Okay, notice here you can see the size of symmetry difference are given to you. Okay, so from the, basically what you do, this size of symmetry difference you write in terms of size of A comma B. Okay, this is the idea. Basically, let me tell you the idea. The idea is this, that what you do, the size of P symmetry difference Q, okay, you find in terms of, okay, you find in terms of size of P, size of Q. Is this clear? So that you can easily do. This is your set P, this is your set Q. Okay, here let me make the Venn diagram. Let me make the Venn diagram. You can see that. Let's again label the areas: area 1, area 2, area 3, area 4. So tell me, what is the size of, in this, I can say in this P symmetry difference Q, which areas are coming? In this P symmetry difference Q, areas 2, 3 are coming. Okay, yes or no? And you can see in this P, which areas are coming? 2, 3 are coming. Sorry, P symmetry difference Q. In this P symmetry difference Q, area 2, 4 are coming. In this P, area 2, 3 are coming. In this Q, 3, 4 are coming. Okay, and you can see in this intersection, in this intersection means P intersection Q, that is your area, that is your area 3. Okay, so you can easily notice one thing here, that if I do size of P plus size of Q, just notice one thing, size of P plus size of Q, then notice what I am doing. This 2 I am counting, this area 2 I am counting one time, area 4 I am counting one time, area 3 I am counting 2 times, and I don't want to count area 3. Yes or no? I want size of P symmetry difference Q. This is what I want, size of P symmetry difference Q. Okay, so notice one thing, that in this P symmetry difference Q, I want to count area 2 one time, area 4 one time. I don't want to count this area 3. So you can see, if I write size of P plus size of Q, then here this area 3 I have counted 2 times. So both these times I have to remove, yes or no? So I have to remove this P intersection Q both 2 times. Both the times I have to remove, yes or no? This P intersection Q I have to remove 2 times. I hope you understood this. Is this clear? See, actually it is very simple. Notice here that this is area of P, this is area of Q. Okay, so if I want to find the symmetry difference, then what that will be? That will be area of P plus area of Q minus this common area we have counted 2 times, in the area of P also, in the area of Q also. This common area 2 times we have counted. Okay, so what you do? Area of P plus area of Q minus 2 times this common area. That will be your size of P symmetry difference Q. Now you can apply this idea. Okay, so very simple point. Here I can say that this P symmetry difference Q, the size of P symmetry difference Q, that will be equal to the size of P plus size of Q minus twice P intersection Q. Okay, is this clear? That's it. Okay, now you can easily apply this formula. You already know A union B union C formula, right? A union B union C, cardinality, inclusion exclusion principle. So what is that? That is size of A plus size of B plus size of C minus intersection, minus size of A intersection B minus size of A intersection C minus size of B intersection C. Okay, and plus size of A union B union C. Is this clear? Very simple. Okay, so this is A union B union C size, the cardinality of A union B union C. Okay, yes or no? Now you can notice one thing, that if I do this addition, just notice, if I do this addition like A symmetry difference B plus A symmetry difference C plus size of B symmetry difference C, if I do this addition, okay, then I am getting 300, right? I am getting 300. But notice one thing, you already know what is this. This is size of A plus size of B minus twice size of A intersection B. Yes or no? So notice here, please notice here, here what you will get, here you will get size of A plus size of B minus twice the size of intersection. Okay, here also the same thing. Here also what will happen, the size of A plus the size of C minus twice the intersection size. Okay, and the same thing will happen here also. Here what will happen, the size of B plus the size of C minus twice the intersection size. Okay, yes or no? So you tell me, if you add all these, then what will happen in this 300? You can see size of A two times. Okay, two times size of A is coming, two times size of B is coming. Actually, you can notice everything is coming two times. Just notice here. You can see that size of A that is coming two times, size of B coming two times, size of C coming two times. Okay, yes or no? Also notice one thing. This value is also coming. Yeah, this is already two times. Okay, this you can see this A intersection B already two times, already two times. This A intersection C already two times, and this B intersection C already two times. So basically, it is happening like this, that everything is coming two times. Which things? Okay, the size of A plus the size of B plus the size of C minus the size of A intersection B minus the size of B intersection C minus the size of A intersection C. Okay, so this is another method, of course. Venn diagram method we have seen. Now this is method number two. Okay, so like this you can solve. Now notice one thing, that what we want here, from here you can you can see one thing, you can notice that, see, okay, for a moment let me forget about it. So you can see that from here, one thing you can notice from here, that size of A, okay, let me write like without these. Okay, you already know, when I write A, it simply means size of A. Okay, so you can see basically we got A plus B plus C minus A intersection B minus B intersection C minus A intersection C. This overall you got equal to 150. Yes or no? Is this clear? This is what you got overall. This value you got 150. Okay, so you can just apply this value here. You can just apply this value here. You can see in this A union B union C, you can just apply this value. Notice this value we already know. This already we have found 150. And this value here, A intersection B intersection C. Sorry. Okay, there is a typo here. There is a typo, that is A intersection B intersection C. Okay, there is a typo here. So this value is 0. Okay, so finally your answer will be what? That will be 150 plus 0. The answer is 150. Okay, so this is another method. I hope you understood this. Okay, so method 1, method 2, both we have seen. Which method did you like the more? Which method did you like the most? Let me know. So I think Venn diagram method, that was quick method. Okay, and many variations you can handle with Venn diagram. Okay, so remember, if you see any set theory question, then one time, if you are not able to solve it, okay, any set theory question, any set theory question comes to you, and if you are not able to solve it, then one time think about Venn diagram. One time think about Venn diagram. Okay, So the Venn diagram, whenever set theory question comes to you, and if you are not able to solve, then the Venn diagram will tell you. Venn diagram will tell you, इधर तो देख. Okay, yes or no? Palat, basically. Palat. अगर इसने गो क्लासेस से पढ़ाई करी है तो पलटेगी जरूर, पलटेगा जरूर. सो बेसिकली द वेन डायग्राम इज सेइंग, दिस इज व्हाट द वेन डायग्राम इज सेइंग. ओके, दैट set theory question is there, so palat. Okay, yes or no? One time you can think about it. Okay, so let's move on now. Let's solve this question from relation algebra DBMS, and this is a very beautiful question. This question is taken from Stanford University, and this is really beautiful question. Okay, so let's solve it. First of all, you tell me, in the AIMT, in the All India mock test, did you solve this question? This relation algebra question from Stanford, did you solve it? Did you get the answer? Did you get the correct answer for this question? We will discuss it. Okay, just give me 1 minute. So, so far, everything you understood? Let me know. Okay. Now, let's solve this question. This question is from DBMS relation algebra. So, let's solve it. The question is saying, suppose we have a relation T. This is the relation. Relation means table. In the database, we have a relation T. PCI, these are the attributes representing the following tree. A tree is given to us. This is not a binary tree. This is actually an array tree. Yes or no? This has how many child? You can see for this node 1. For this node 1, we have total 5 child. Okay. For this node 2, we have 2 child. This node 3 does not have any child. Node 4 has 1 child. Node 5 does not have any child. Node 6 has 1 child. Okay. So the question is saying that T, PCI, this is a relation representing the following tree. So how this tree is represented by this database relation? This is written here. Okay, you can see the nodes are distinct integers. In this tree, the nodes are distinct integers. You can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and you can see the meaning of a tuple in this table, in this relation. When you have a tuple PCI, small p, small c, small I, so the meaning of a tuple in this table T is that the node C is the ith child of node P. Notice one thing, that in this table, when you have a tuple, then it means that this node C, this is ith child of node P from the left. Okay, from the left. Read this line also. From the left. Attribute C is the primary key in this T. In this table, the attribute C, that is the primary key. For every node except the root, we have a tuple in T. Okay. So first, what you do, you understand this complete statement. First, we will try to understand. Okay. Then we will solve this question. So first, you try to understand this complete statement, how this table is created. Okay. So you can see that this tree we have. Okay. So notice one thing. We are saying that any tuple PCI means this C is ith child of P from left. Okay. So you can notice that in this T, in this table, PCI, in this table, what are the tuples that we have? Okay, let's see the tuples that we have in this table. So you can see that in this table, I can have a tuple like, for example, you can see this 2. This 2 is first child of 1. Yes or no? Notice this 2, this is the from the left. This 2 is the first child of 1. For this 2, the parent is 1. And you can see this 2 is the first child of 1. Okay, just read this point. Notice that node C is the ith child of node P from the left. Okay, basically in this table, we have this table PCI. In this table, notice one thing. If you have this type of tuple, for example, here you have X, here you have Y, here you have Z. Okay, then notice one thing. Here basically, this X is the parent of Y. Okay, please understand. Here, notice one thing, that this X is the parent of Y. So let me tell you here. X is parent of Y. Yes or no? X is parent of Y. Also remember, this Y is the ith, or I can say jth child of X. Okay, and remember, Y is the jth child of X from left. Okay, so it is like this, that this 2, for this 2 the parent is 1, and this 2, this is the first child of 1. Okay, yes or no? So this tuple will be there, 1 to 1. Do you agree with me? See, writing the tuple is actually very easy, because you can see that basically you just write a node here. Notice, here you write a node, and here its parent, and here what you do, here you say that this X is which child of X. This y is which child of X from the left. Okay, so for example, tell me, will there be any entry for 1? For this root node, will there be any entry? What do you think? For this root 1, for this root node, can you make any entry? Can you make any tuple for the root node? No, there will be no tuple for the root node. Why? What is the reason? Because there is no parent for the root node. For the root node, there is no parent, so there is no tuple for the root node, and that is written here, that for every node except the root, there is a tuple. Okay, yes or no? For this node 3 also there is a tuple. For this node 3, what I can say? For this 3, the parent is 1. And this 3 from the left, this 3 is basically second child of 1. Yes or no? For this 4 also I can say that this 4 is child of 1, third child from the left. Yes or no? Next, you can see for this 5 also, what I can say? For this 5, I can say that this is a child of 1 and fourth child from the left. Next, you can see like this. Okay, like this. Also, you can see, for example, for this 8. Okay, for this 8, what I can say? For this 8, what I can say? I can say that the parent is 2, and this 8 is the second child of 2. Is this point clear? So the table, did you understand? You don't have to write the table, but did you understand the table? In this table, tell me how many entries will be there? We have this table P, C, I. Okay, this P represents parent. P for parent. C for child. I for which child? Okay. Which number of child? Which number of child from left? Okay, so is this clear? P means parent, C means child, and here remember this C, this is the primary key that is already given to you. You can notice in this question it is saying that C is the primary key. Okay, means for these children, for the child, these are the child of someone. This root node has no parent, so this root node is not a child of anyone. This root node, this is not a child of anyone. So that is the reason, remember, for these people who are child of someone, for these people we make a tuple. For the root node there is no tuple. Okay, yes or no? And this C is the primary key. Tell me how many tuples will be there in this table? Let me know. In this table you will have this type of tuple. For example, for this node 9, there will be a tuple for node 9, and the parent is 4. And you can see from the left, this 9 is which child of 4? That is the first child of 4. Yes or no? Notice one thing. For this 4, there is only one child. Okay, so don't say 2. Don't say that it is the right child. There is no left child, remember. Okay, so this is the only child. That is the reason I can say like this. Okay, anyway, don't worry. This does not affect the question. Okay, this thing does not affect the question. Is this clear? This will not affect the question. You can see for this 10 also, for this 10 also, the parent is 6, and this 10, this is the first child of 6. This 10 is the first child of 6. Yes or no? And so on. You can see for this 5, we will have like this 1, and this 5 is the fourth child. Yes or no? Okay, and so on. I hope you understood. So tell me how many rows will be there? Like if I ask you what are the number of rows in T, in capital T, that will be equal to how many people have parent? Yes or no? So that will be basically, you can see 5 and 4, 9. So these many rows will be there in this T. 9 rows. Okay. Anyway, this is just to understand the question. I hope you understood this first thing. Now, what this question is saying, notice. Now the question is saying that there is a relational algebra query which we are making on the database. Database means the table T, PCI, yes or no? Okay, so on this table, on the database containing this table, on that database, we are making this relational algebra query. Okay, we have R1, we have R2, then we have R1 minus R2. Okay, this R1 minus R2, that is your answer. And the question is asking the number of rows in the answer. So what we need to do to solve this question? We need to understand what is R1. First, we need to understand this R1. Okay, like this query is for what purpose? Then we need to understand this R2. This query is for what purpose? What will be output of R1? What will be output of R2? Then we need to do R1 minus R2. That's it. Okay. So one thing I want to tell you, don't run this R1, don't run this R2 on this tree, because remember, in your table you have total 9 tuples. Please understand. In the table you have total 9 tuples. So if you run this query, this R1 query, if you run on this 9 tuples, also this R2 query, if you run on these 9 tuples, it will take a lot of time, because notice one thing. In this R1, we are doing one natural join. Yes or no? And in this R2, we are doing two natural join. In R1, one natural join you are doing. In R2, two natural join you are doing. So basically, if you blindly, like if you apply the brute force method, and if you run these queries on this table, on this tree, if you directly run this query, then it will take a lot of time. The best method, that is, you understand these queries. That is the best method. Okay, so now we will try to understand these queries. So first we will try to understand the query R1, then we will understand query R2, then we will see R1 minus R2. Okay, so first you try to understand this query R1. In this query R1, notice what we are doing. We already have this table T, which has attributes PCI. P means parent, C means child, I means the position from left. Okay, this I means position from left. Child position from left. This C means child. This P means parent. Okay, so very simple. Child position from left. Okay, so now here you can notice what we are doing. We are doing the natural join. Okay, of this table we are taking two times. Okay, and you can see renaming we are doing. So renaming of table we are doing, and the renaming of some attributes also we are doing. Okay, so focus here, focus here. Here you can see that a table T1 I am taking. In this table T1, which attributes I have? Parent P is same C1 and I1. Okay, and I am also what I am doing, notice here, that this table T2 I am taking, table T2. Okay, renaming, basically we are doing the renaming of this table T. So you can see this table T2 I am taking. Here I have P C2 I2. Okay, now what the next step? You can see we are doing the natural join. Natural join means what? Natural join simply means equality of all attributes with the same name. Yes or no? Okay, already you can see that this is natural join. Natural join means equality of common attributes. Equality of common attributes. Okay, so equality of common attribute, that simply means that this p1 should be, this p should be equal to this p. Parents should be same. Yes or no? Agree? So remember, parents same. This is the one thing we got to know. Very good. Step by step we are going. We understood that okay, parents should be same. Is this clear? This p should be equal to this p, because you can see there is a natural join. Natural join means equality of common attributes. Okay, equality of attributes with the same name. Here you can see that this p and this p, they are attributes with the same name. Okay, so here their equality we want. Next, you can see that also what we want those tuples. Here there is a select. Okay, you can see tuple selection. You can see we have tuple selection. Okay, in the tuples, basically whatever tuple you have. Okay, let me tell you which type of tuple we want. I will tell you, don't worry. But the point is that in the tuple that I want, this I2 should be greater than I1. This I2, this should be greater than I1. Okay, then finally, what I want C1, C2 projected. Okay, here you can see attribute selection. Okay, yes or no? We are doing the attribute selection, projection, attribute selection. So basically, finally in the output, this C1, C2 in the output. Okay, output will have C1, C2. Okay, basically this will be there in the output. I hope you understood. This is the schema of the output. Is this clear? Let me know. Now let me tell you. Basically, what is happening here is that which type of tuples I want. See, because you will do natural join. We are doing natural join, right? Okay. So in the natural join, what will happen? Which type of tuples I want? I want this type of tuples here. I want this type of tuple where this parent is same. Okay, remember this parent is same means, for example, here if you have value x, here also you must have value x. Okay, the parent must be same. The parent, they must be same. And what else I want? I also want that if this value is, let's assume, for example, if this value is 4, then this value can be 6. Yes or no? Is this clear? So basically what I want here between these, I want greater means this value and this value. Okay, I can say like this. For example, if I take a value I here and if I value j here, then remember this I must be less than j. Okay, and then that's it. This is what I want. Okay, that's it. Okay, then whatever I have here, they will go in the output. Okay, is this clear? They will go in the output. These two people, they will go in the output. That's it. I hope you understood this point. Okay, so can anyone tell me what is the meaning of this query R1? In this query R1, basically from the tree point of view, what we are doing? From the tree point of view, what we are doing? Basically, we are making sure that parent is same. See, I am taking those C1, C2 which have same parent, and C1 is to the left of C2. Okay, do you agree with me? C1 is to the left of C2. Okay, so basically here I can say that in this query R1, okay, let's see output of R1. Okay, output of R1, that is C1, C2. Okay, and here let me tell you that C1, C2 have same parent. C1, C2 have same parent. What it simply means? It simply means that C1, C2 are sibling. C1, C2 are sibling. C1, C2 are siblings. Is this clear? So C1, C2 have same parent means they are basically sibling. And one more thing, that the position from the left, the position of C1 should be less than position of C2. It means that C1 is to the left of C2, to the left of C2. May not be immediately, not necessarily immediately. Yes or no? Not necessarily immediately. Not necessarily immediately. Basically, the point is that the from the left, the position of C1 should be less than position of C2. So C1 is to the left of C2, not necessarily immediately. Okay, and C1, C2, they have the same parent. That's it. So now you can tell me what will be the output of R1. Can you tell me quickly? Now you can notice that you don't have to run this query R1 on the table T. Okay, you can logically understand what this query is doing, and now you can tell me the output. So what will be the output? Output will be the siblings. That's it. Okay, remember, output will be the siblings. That's it. Siblings. These are the siblings with, okay, these are the siblings with C1 to the left of C2. Okay. If you think that if this is the first child, second child, third child, it simply means that C1 is elder than C2. Yes or no? C1 is the elder sibling of C2. Okay, so finally tell me how many rows will be there in this R1? In this R1, you can notice there will be 2, 3. These are the siblings. Will we have 2, 8? Do we have 2, 8? No, we don't have. 2, 3 are sibling, and you can see 2 is to the left of 3. 2, 4. Next, 2, 5. Yes or no? You can see 2, 3, 2, 4, 2, 5, 2, 6. Okay, of course, there will be many more. Okay, you are understanding the point. So for example, there will be 3, 4, there will be 3, 5, there will be 3, 6. Okay, yes or no? And so on. Dot, 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 dot. Okay, you can see dot, dot. And then you tell me what else. Then, for example, there will be 7, 8 also. Yes or no? That's it. Okay, so tell me in this R1, how many tuples will be there? What will be the number of tuples? Can you tell me? What will be the number of tuples? Actually, you just tell me the number of tuples in R1. Let me know how many tuples in R1. Very simple. Remember, from the two point of view. Okay, from the two point of view, we have 1, 2, 3, 4, 4 tuples for 2. Okay, 4 tuples for 2. Then 1, 2, 3, 3 tuples for 3. Okay, so you can see 4 plus 3, that is 7. Yes or no? 4 tuples, then 3 tuples. Then you can see for this 4, we have 1, 2 tuples for 4. Okay, then you can see for this 5, we have 1 tuple. And then you can see for this 7, we have 1 tuple. Okay, then you can see for this 8, we don't have any tuple. Remember, because 7, 8, we don't have 8, 7. We have 7, 8. For this 9, there is no tuple because there is no sibling. 9 does not have a sibling. 10 does not have a sibling. Yes or no? 9 comma 10, they do not have sibling. So that's it. Finally, you can see this is 7. So 11. Yes or no? You can see the number of tuples in R1, that is basically 11. Okay. Now let's see R2 also. The way we have understood R1, let's try to understand R2 also. Okay. So in this R2, you can notice we are doing two natural joins. Okay. So let's try to understand this R2. You can see in this R2 what I'm doing. We have this table T. Remember, in this table T we have P, C, I, and you already know that this P is the parent, C is the child. Okay, and this I is the child position from the left. Okay, so now you can see we have, notice what we are doing here. Here notice we are renaming this table T T1. We are renaming this table T T2. We are renaming this table T T3. Okay, so basically we have three instances of table T. Okay, yes or no? Three instances. We have table T1 where we have parent again is same. Notice P C1 I1, P C2 I2, P C3 I3, P C1 I1. Okay, then again, then you can see T2. In this T2 we have P C2 I2, and in this T3 we have what? In this T3 we have P C3I3. Okay, correct. Now you can see we are doing the natural join. What the natural join means? See, I am doing the complete analysis. That is the reason I am taking time. But actually, this question will not take time if you solve it by yourself. Okay, I am just explaining every point. Okay, the meaning of every symbol, the meaning of every dot also. So you can see that we are doing the natural join. Natural join means what? This means equality of common attributes. Yes or no? Equality of common attributes. The equality of common attributes. Okay, yes or no? This is what this natural join means. Equality of common attributes. What it means equality of attributes with the same name. What are the attributes with the same name here? We are doing the natural join. Notice this natural join we are doing. Okay, so tell me, this natural join we are doing. Now you tell me, what are the attributes with the same name? This p is the attribute with the same name. So what I want equality of the attributes with the same name. Yes or no? So notice, basically I want these people, these to be equal. I want them to be equal. They must be equal. Okay, what else I want? Then you can see we have this tuple selection condition. Here we are doing the tuple selection. Okay, from T1 natural join, T2 natural join, T3. From this we are doing the tuple selection. And here you can see that I2 I want greater than I1. Notice, I want what I want that I2 must be greater than I1. Okay, this I2, this must be greater than I1. Also, what I want, you can see, I want that, and there is and here, there is and here, and I3 must be greater than I2. This I3 must be greater than I2. Yes or no? This I3 must be greater than I2. Okay, so basically I can say that I1 must be less than I2, must be less than I3. This is what I want. Okay, this is what I want, because there is and here. Okay, here there is and. So this is what I want. And finally, this is the attribute selection. Which attributes I am selecting? We are projecting the attributes. Which attributes we are projecting? We are not projecting C1, C2. We are not projecting C2, C3. We are actually projecting C1, C3. Okay. We are saying that, okay, you come to me. And we are saying you also come in the output. Okay. Yes or no? These are in the output. C1, C3 are in the output. Is this clear? So basically, can you understand the meaning of this query R2? This query R2 is basically saying that, notice one thing, this C1, C2, C3, they have the same parents, so they are actually sibling. But I am saying that I want C1, C3, and they, between them, there is another child. This is interesting. Means C1 is not immediately left to C3. Yes or no? Between C1, C3, there is at least one child. Okay, yes or no? So they are not immediate sibling. I can say they are not immediate sibling. I can overall, what I can say, let me tell you. Overall, I can say that here, here I can say this R2, meaning of R2. Let's see meaning of R2 query. In this R2 query, you can notice the output is C1, C3. This is the output. Okay. And you already know that these are basically siblings. Here, these C1, C3, they are also siblings. Why they are siblings? Because they have same parent. Same parent. Okay, so you can see that basically we have siblings, but not immediate siblings. But not immediate siblings. But not consecutive siblings, I can say. Okay, is this clear? Not consecutive siblings. But not consecutive siblings. Okay, this C1, C3, these are siblings, but not consecutive siblings. It's like this, that there is C1, there is C3, and there is at least one sibling in between. Okay, there is at least one sibling in between. It is like this. You can see it is like this, that this child C1, this child C3, and there is C2 here. Okay, it is this type of situation. for the position. Okay, for their position means this I1, this I2, this I3, and here you have C3. Okay, and this is what I want. I hope you understood this point. So siblings I want siblings, but not consecutive siblings. And also one more thing, remember, C1 elder than C3, or I can say C1 to the left of C3, but definitely not immediate left. Okay, yes or no? Not immediate left, because I don't want consecutive siblings. Okay, so I can say not immediate left, not immediate left. That's it. So from your understanding, what do you think? How many tuples are there in R2? What do you think? How many tuples we have in R2? In this R2, how many tuples we have? C1, C3. You can see. Okay, so how many tuples are there? Very simple. Notice there will be 2 4. Yes or no? There will be 2 4. There will be 2 5. There will be 2 6. 2 4, 2 5, 2 6. Okay, what else we have? We have 3 5 3 6. 3 5 3 6. What else we have? We have 4 6. Yes or no? We have 4 6. Okay, that's it. You can see they are consecutive siblings. This does not have any sibling. This does not have any sibling. Okay, yes or no? That's it. So this is your R2. So what are the number of tuples in R2? Number of tuples in R2. So that is basically total 6. 6 tuples in R2. Is this clear? Now we understood what is R1. We understood what is R2. So what is R1 minus R2? Did we understand? You can see what is R1. R1 is basically siblings. Okay, yes or no? R1 is basically siblings. R1 is giving me siblings. And R2, what it is giving me? It is giving me siblings, but not immediate siblings. It is also giving me siblings, but not immediate. But not immediate. Okay, yes or no? But not consecutive, I can say. Okay, R2 is also giving me siblings, but not consecutive. Okay, is this clear? So tell me now, if I do R1 minus R2, what I'm going to get? If I do R1 minus R2, what I will get? R1 is giving me siblings, all the siblings. Okay, R2 is giving me siblings, but not consecutive. So R1 minus R2 will give me what? It will give me consecutive siblings. That's it. That's it. Consecutive siblings. Okay, that's it. So finally, what will be the number of tuples in R1 minus R2? You can see answer. Answer is same as R1 minus R2. And in this R1 minus R2, how many tuples we have? What will be the number of tuples? Basically, in this, what you have? You have immediate siblings. There is 2, 3. There is 3 consecutive siblings you have. Okay, yes or no? We have consecutive siblings. 3, 4. There will be 4, 5. There will be 5, 6. There will be 7, 8. Okay, yes or no? You can see 2, 3, 3, 4, 4, 5, 5, 6, 7, 8. That's it. So you can see total 5 tuples. So the number of tuples, that is basically 5. Okay, that's your answer. I hope you understood. Okay, so this is the complete analysis of this question. I hope you loved this question. This is really a beautiful question. You can see, and remember, this type of questions, they can obviously they can come in the gate exam, right? This type of beautiful question, they can actually give you, they can give you a tree. Okay, some structure they can give you. This can be a graph, this can be a tree. These are the variations possible. I'm telling you, these are the variations possible, that they can give you tree, they can give you graph, and then they can give you some query like R1, R2, some query they can give you, basically some query. And this query, what it can find? For example, it can find consecutive siblings. It can find siblings but not consecutive siblings. It can find all the siblings. Okay, for a graph, maybe it can find adjacent nodes. Yes or no? Some variations. What are the possible variations? What are the possible variations? Don't worry, I will not give in the upcoming AIMT. Already one question I have given you this in this AIMT. In the All India mock test one, this question I have already given to you. Now remember, from this question, from your understanding, after the analysis of this question, the improvement, or I can say the understanding that you got, okay, now based on that you can solve any variation. Okay, any variation if they ask you in the gate exam. For example, in the gate exam, what they can give you, they can give you input as, for example, they can give you input as a particular graph they can give you. Okay, a graph. Is this clear? And then they can give you some query. What are the possible query? This query can be relational algebra query, or this query can be SQL query. Yes or no? And maybe the output will be something like this. The output will be maybe adjacent nodes. Okay, yes or no? Maybe the output will be something like adjacent nodes. Okay, maybe, like for example, or maybe the output will be non-adjacent nodes. Okay, something like this. Or anything they want. Okay, yes or no? Or what gate wants. So I hope you understood that many variations you can handle in the same way. Okay, I hope this is clear. So let's move on now. Let's solve this question from DBMS SQL. And in this question, you can see C1, C2, C3. These SQL queries are given to us. And we have a relation. We have a table R. You can read this here. We have a relation table R with 4 tuples. These are the tuples. You can see there are some tuples which have null also. You can see some tuples have null also. And the question is saying that in which the first, second, and third values, they refer to attributes 81, 82, 83. Basically, in this table R, what is the schema of table R? So let me tell you here. Basically, the schema of table R, it is like this: that the first attribute, that is 81, the second attribute is 82, the third attribute, that is 83. Okay, this is the schema of table R. And in this table R, what you have? You have these tuples, like you can see 12, 15, 5100. Okay, then you have 13, there is null, and then there is 3500 some value. Then you have 14, null, null. Okay, and then what we have? We have 15, 12, null. Okay, so you can see that these are the attributes. The first value, the second value, the third value, in each tuple they refer to attributes 81, 82, 83 respectively. The following commands represent queries on R. So we have 3 SQL queries on R: C1, C2, C3. The question is asking the number of tuples returned by the execution of commands C1, C2, C3 respectively. What will be the number of tuples in the output of query C1? What will be the number of tuples in the output generated by the query C2, and so on for C3 also? Okay. So basically, in this question, you can notice one thing, that there is some game of null. Okay. So what concept we need to know to solve this question? What are the concept that we need to know? The concept is actually very simple. The concept is that in the SQL, okay, the SQL concept you already know, that if you perform arithmetic operation with null, then the result will be null. So remember, if you perform arithmetic operation with null, okay, here this hash can be any arithmetic operation null, okay, and this can be y. Then here you can see the result will be null. Okay, so here you can notice what is this? This is some arithmetic operation. Okay, this is the first concept, that arithmetic operation with null, the result will be null. The second operation, if you perform comparison with null, okay, what I mean by comparison? Comparison means, for example, greater than equal to, less than equal to, greater than, less than, greater than equal to, okay, greater than equal to, less than equal to, not equal to. Okay, so like this, these are the comparisons. So you can see that etc. So comparison with null is is it null? Can I say comparison with null is null? No, no, no. Comparison with null, that is unknown. Okay, comparison with null, that is unknown. This is a third truth value. This is a third truth value in SQL. In SQL, this is third truth value. There are three truth value in SQL. Okay, in SQL, if you notice, in this SQL, there are three truth value: true, false, unknown. Okay, is this clear? So basically, SQL uses three valued system. This SQL, this is a three valued system. Okay, anyway, you can see that your standard Boolean algebra, that has true comma false only, that is a two valued system. Your standard Boolean algebra, that is a two valued system, it has truth value true comma false. But in SQL, we have three truth value: true, false, unknown. And remember, comparison with null, that is basically unknown. Okay, one more concept we need. What is that? One last concept that we need to solve this question, that is this, that if you perform AND operation with null, AND operation, remember, okay, just let me tell you the trick, that X and Y. Now here, remember, this X comma Y, they can, this X can be, for example, true, this X can be false, this X can be unknown. Similarly, this Y can be true, this Y can be false, this Y can be unknown. Okay, is this clear? This Y can be unknown. So you can see that if I have X and Y, then what that will be? That will be basically minimum of X comma Y. Okay, this is a trick. What to do? You assume that this T is same as 1, this F is same as 0, and this U is same as half. Okay, this is what you assume. Okay, that T means 1, F means 0, and this U means half. Okay, so this is just a trick, remember. This is just a trick. This is not a concept, this is just a trick. It is not a concept, it is just a trick. And but remember, this trick is actually used as a concept. Okay, this is given in the Ullman book also, this trick. So remember, this is just a trick, this is not a concept. And one more thing, that this trick is used as a concept because this is also given in the Ullman book, this trick. Okay, now let's see. So you can see X and Y, that will be basically minimum of X comma Y. Similarly, if I ask you what is X or Y, that will be maximum of X comma Y. And if I ask you what is negation of X, then that will be 1 minus X. Okay, that's it. So now we understood all the concept that we need to know to solve this question. Now let's solve this question. So one by one, all the three queries, let's understand. Let's focus on the query C1 only. You tell me about the C1 query. What will be the number of tuples in the output generated by the C1 query? Here you can see what we are doing. Select star from R. So this is your table R. Now where? Basically, where means those tuples. We are selecting the tuples here. So those tuples we will select where this condition becomes true. One more thing, let me tell you here, a small thing, let me tell you that in the SQL, a small thing, let me tell you, in the SQL, see, if you have this where clause, if you have this where clause, in this where clause, there is a condition. Okay, yes or no? There is a condition. In this where clause, we have a condition. Condition C. So this is the situation that in the where clause we have this condition C. So let me tell you that if this condition C for any tuple T, for any tuple T, okay, for any tuple T, if this condition C becomes false, then remember T will be rejected. Okay, the tuple T will be rejected. It will not go in the output. The tuple T will be rejected. Is this clear? If this condition becomes true, then remember T will be selected. Okay, T will go in the output. Okay, and remember, if this condition is unknown, the third truth value, if this condition is unknown, then also this tuple will be rejected. Okay, is this clear? So remember, the tuple will be selected, the tuple will be sent to the output only if and only if the condition actually becomes true. This where condition, this must become true. If this condition is unknown or false, then that tuple will be rejected. Okay, is this clear? I hope you understood. Now you can easily solve this question. So tell me here, we have a condition here. So first of all, you tell me what about the first row, 81 greater than equal to 12. Here, for which row we have 81 greater than equal to 12? Like, okay, let's check the first row. Let's check this condition. 81 greater than equal to 12? Yes. Okay, for the first row, let's call it T1. For the first row, 81 is greater than equal to 12. Yes, this condition is true. What about this next condition? 82 greater than 14. Yes, that is also true. True and true. You can see this is also true. This is also true. True and true. That is true. So for this tuple, this where condition has become true. So this tuple will go in the output. Okay. Let's see what about this tuple T2. What about tuple T2? You can see 81 should be greater than equal to 12. Yes, 81 is greater than equal to 12. And what about this 82? 82 greater than 14. 82, that is null. Null greater than 14. Null greater than 14, that is comparison with null, that is unknown. Yes or no? Comparison with null, that is unknown. So let me tell you for T2, just focus on T2. Explanation for T2. I am telling you explanation for tuple T2 in query C1. Okay. So here you can see that for this tuple T2, what will happen? For this tuple T2, it will happen that this 81 greater than equal to 12. Yes, that is true. True, and you can see 82, that is null. Null greater than 14. Comparison with null, that is unknown. Okay, yes or no? So what is T and unknown? What is that? T and unknown. True and unknown. I told you that is basically minimum of T comma U. Remember U is half. Okay, remember U is half and T is 1. Yes or no? T is 1 and U is half. So here what you will get? You will get half, minimum of 1 comma half. What is that? What is minimum? That is half. That means unknown. Okay, you got unknown. So in the where, if the condition is unknown, then what I can say? The tuple rejected, yes or no? So from here I can say that T2 rejected. Is this clear? So please understand that T2 will be rejected. Okay, now let's quickly do. What about this T3? This tuple T3. 81 greater than equal to 12. Yes, this condition is true. Okay, this is true. And 82 greater than 14. Again, you can see that null, comparison with null, that is unknown. True and unknown, that is unknown. So this also will be rejected. This tuple T3, that will be rejected. What about the tuple T4? 81 greater than equal to 12. 15 greater than equal to 12. Yes, that is true. So this has become true. And 82 greater than 14. 12 is greater than 14. No, that is false. False and true. That is false. So this tuple T4 also will be rejected. Okay, yes or no? So I can say that number of tuples in the output generated by this query C1, that will be only one tuple in output. One tuple in output. Okay, is this clear? Very simple. Okay, let's see the next query. What about C2? What about C2? Notice one thing, just look at the options. In the options, you can see that this C1 will generate one tuple. So these two options, option A, comma B, are gone. Okay, now you can just check C2. You don't even have to check C3. Okay, you can save time because you can see only these two options are remaining after C1. Now, what you can do, you can just check C2. Okay, just check C2. That would be enough. So you can see, let's check C2 here. So we have these tuples T1, T2, T3, T4. Okay, so you tell me quickly, what about tuple T1? Again, we have select star from R. This is the table R. Now where 82, here you can see in this query C2, notice 82, 83. Only these we care about. Okay, yes or no? We only care about 82, 83. Okay, so I don't want confusion. That is the reason I'm removing this 81. Okay, because I don't want confusion. Because you can see in this query C2, we only care about 82, 83. Okay, so you can see 82 in this. Let's check this tuple T1. I am checking the tuple T1. 82 greater than 12. 15 greater than 12. Yes, that is true. This is true. Okay, what about 83 greater than 3000? 83 greater than 3000. Yes. So true or true? That is true. Yes. So this tuple will go in the output. Okay, next, what about the tuple T2? You can see for this tuple T2, you can see 82, that is null. Null greater than 12, comparison with null, that is unknown. Okay, so let me tell you the explanation for tuple T2. Again, here also, let's quickly see explanation of tuple T2. You can see that for this tuple T2, this comparison with null, this will become unknown. Okay, for the tuple T2. So you can see for this tuple T2, what you will get? You will get unknown or this 83 greater than 3000. 83, that is greater than 3000. Yes, that is true. Unknown or true. Remember, unknown or true. That means what? That means maximum of u comma t. Yes or no? This is or. So here what you will do? Here you will take maximum of u comma t. Remember, u is half and t is 1. What is the maximum of these two? That is 1. That means true. Okay, so I can say that basically you got u or t, unknown or true. So that will become true. So that is the reason I can say this where condition has become true. So this tuple T1, this tuple T2, this tuple T2 will be selected. Okay, yes or no? So I can say tuple T2 selected. Very simple. So remember here, this tuple T2 also will be selected. Very good. Okay, now let's see quickly. What about the rest? What about T3? Tuple T3. 82 greater than 12. Comparison with null, that is unknown. And you can see 83 greater than 3000. Comparison with null, that is unknown. Unknown or unknown, that is unknown. Yes or no? So that is the reason this T3 will be rejected. Okay, what about this T4? You can see 82 greater than 12. 12 greater than 12, that is false. What about this 83 greater than 3000? Comparison with null, that is unknown. False or unknown? What is that? Let me know. What is false? False or unknown? So remember, or simply means max. You are taking max. Max of f comma u. F means 0, u means half. So that is basically u. The overall point is that this where condition has become unknown, so this tuple will be rejected. Okay, so you can see that for this C2, I can say two tuples in output. So at this moment, you can stop and you can say that the answer will be option D. Okay, of course, you can check this query C3 also. Okay, let me quickly check the query C3 also. So now I am checking the query C3. Let's quickly do this. In this query C3, we have negation. Okay, so you can see in this query C3, I only care about 81, 82. So I don't want confusion. So I'm removing this 83. I don't want confusion. Okay, so that is the reason. Now you can see that here, it. Let's check all these tuples. This tuple T1, let's check. This tuple T2, let's check. This tuple T3, let's check. This tuple T4, let's check. Remember one thing, that this where clause will check tuple by tuple. Okay, yes or no? This where clause. This checks. This checks tuple by tuple. Okay, tuple after tuple it will check. So let's check for tuple T1. You can see we have 81 81 less than 82. Okay, so 12 less than 15. Yes, that is true. Negation of true, that is false. So this tuple T1 will be rejected. Okay, yes or no? Next, you can see for this tuple T2, let's check tuple T2. 81 less than 82. Comparison with null, that is unknown. What is negation of unknown? Negation of unknown, that is also unknown. Okay, so I can say this also will be rejected. Next, you can see 81 less than 82. So comparison with null, that is unknown. Negation of unknown, that is unknown. So this also will be rejected. What about this? You can see 81 less than 82, 15 less than 12, that is false. Negation of false, that will be true. So this T4 will be in the output. Okay, so one tuple will be in the output. I can say here what we can say that one tuple in output. Okay, that's it. This is the complete analysis of this DBMS SQL question. I hope you understood. So far, each and every question, did you understand? Please tell me. Let me know. Each and every question. Understood so far? So, what do you think? Like, so far, all the questions, are you learning from them? Like, are you thinking that, yeah, these are good questions? See, a lot of effort has gone into, making this all India mock test one. To make any mock test in the Go Classes test series, whatever mock test, whatever AIMT, okay, anything that we make, okay, a lot of time we spend so that we can provide you, good 65 questions. Okay, the gate pyqs you can solve from the gate pyqs, but then when you come to Go Classes test series, when you come to Go Classes weekly quizzes, when you come to Go Classes AIMTs, mock test, topic wise test, subject wise test, then you must learn a lot. Okay, yes or no? Pyq you can solve from the gate pyq boot, from the gate overflow. Okay, you can see there is a gate overflow PDF, right? There are gate overflow PDFs for gate pyqs. So from gate overflow PDF you can solve all the gate pyqs you can solve. Okay, and then for the future gate exam, new questions will come. Yes or no? In the future gate exam, new questions are going to come. So if you want to solve new questions, some good variations, some good quality variations, then you can come to Go Classes test series. You can come to Go Classes all India mock test, topic wise test, subject wise test, quizzes. A lot of things are there. Okay, so I hope you are loving this. I hope you are loving this session so far. Okay, so far everything is clear. Let's solve this DBMS question based on decomposition. Consider the attribute. Consider the attribute set R. So this is a relation. We have this relation schema A, B, C, D, E, F. These are the attributes in the relation R. The functional dependency set. This is the set of functional dependencies. A Go classes student decides to write a decomposition table. See, a Go classes student decides to write a decomposition of tables as ABDE, ABCF. Okay, basically, for this table, a Go classes student is writing a decomposition, decomposing this table into ABDE, ABCF. First of all, you tell me, is this a valid decomposition? When I ask you valid decomposition, it simply means, is the attributes preserved? Did we preserve the attributes? Did we lose the attributes or not? You can see we have A, B, C, D, E, F. These are the attributes in the table R. And here also we have A, B, C, D, E, F. All the attributes we have. So remember, yes, this is a valid decomposition because attributes are preserved. Okay, now let's see. Right now, this is not a lossless decomposition. Why this is not a lossless decomposition? Because if you find the common attributes, the set of common attributes, that set of common attributes is not a super key in any of them. Okay, that is the reason this is not a lossless decomposition right now. Which of the following changes, okay, these changes we are applying individually, means we have to consider these changes individually. Okay, you cannot combine them. Okay, all these three options you have to consider individually. So you can see which of the following changes, when they are applied individually, not combined together, would make this decomposition lossless. Okay, so this is a very simple question actually. What concept you need to understand to solve this question? What concept we need to solve this question? Very simple. Remember, whenever you have a binary decomposition, here you have a table R and you are decomposing this into table R1, R2. Okay, So this is called binary decomposition, because I'm decomposing the table R into two sub relations. This relation R I'm decomposing into sub relations R1, R2. So this is called binary decomposition. And let me tell you that for this binary decomposition, is this decomposition lossless or not? The decomposition is lossless or not? When can I say a decomposition is lossless? Decomposition is lossless. What it means? It means that when I combine this R1, R2, then I will get exactly this R. Okay. No false information I will get. This is the definition of lossless decomposition. Lossless decomposition means, see, this table you have divided, you have decomposed into sub relations R1, R2. This decomposition, this is a binary decomposition. This decomposition will be lossless if and only if for any instances of R1, R2, whatever instances of R you take, whatever instance of R1, R2 you take, then remember, if I combine, means if I do the natural join, okay, if I do the natural join of R1, R2, then I must get exactly this R. The natural join of R1, R2 must be equal to this R. Then we will say that it is a lossless decomposition. And remember, if the natural join of R1, R2 is proper superset of R, means you are getting some false information, some spurious tuples you are getting, then in that case it will be called lossy decomposition. Lossy decomposition means that when you do the natural join of the decomposed relations, when you do the natural join of the sub relations, then you may get, it is possible that you may get some extra tuple which is not in R. Okay, this is called spurious tuple, and this type of decomposition is called lossy. So here you can see this is a binary decomposition. When can I say this decomposition D, this decomposition D, when can I say this decomposition D is lossless? This decomposition D is lossless if and only if there is a simple method. What you do? This decomposition is lossless if and only if you find R1 intersection R2, means the set of attributes common in R1, R2. Okay. So you find the set of attributes common in R1, R2. So this R1 intersection R2 you find. This R1 intersection R2 is a super key, is a super key in R1 or R2. Or I can say that this decomposition is lossless if and only if this R1 intersection R2 either derives R1 or it derives R2. Okay. So this R1 intersection R2 derives R1, or this R1 intersection R2, this derives R2. Okay. So very simple point. I hope you understood. Means this R1 intersection R2, this set of attributes common in R1 comma R2. So this R1 intersection R2, this is basically a super key in at least one of them. Okay, yes or no? So first let's check. The question is saying that right now this decomposition is not lossless. Why? What is the reason? See, the question has given you this information that right now this decomposition is not lossless. What is the reason? Because you can see this is R1 your, this is the subrelation R1, this is the subrelation R2. What are their intersection? R1 intersection R2. When I say intersection, I am talking about the schema intersection. Okay, here remember this intersection, this R1 intersection R2, this is the schema intersection, means this is the set of attributes common in R1 comma R2. Please understand, this is the schema intersection. This is not the intersection of the instances. We are not taking the intersection of tuples. Okay, we are not taking the intersection of tuples. We are taking the schema intersection. Basically, what are the common, what is the set of common attributes? Okay, so this is schema intersection. Anyway, so here you can see what is this R1 intersection R2, ABDE, ABCF. So that is basically AB. Okay, now what you do? You see, can AB determine ABDE? Can AB determine ABCF? You just check this. Can AB determine ABDE? Okay. Can AB determine ABCF? If any of them happens, this happens or both happen, then we will say that this decomposition is lossless. Okay. So what you do? Here you check what is AB closure. Okay. Let's see what AB can determine. So let's find AB closure. So what is AB closure? What AB can determine? You can see AB will definitely determine AB, of course. Okay. So you can see AB will determine AB by the reflexive property. Yes or no? So you can see A is also determining B, but that we have already written. Next, you can see B is determining EF. Very good. So AB will also determine EF. Now, this AB EF, what it can determine? Nothing. This F also can determine A. F also can determine A. Okay, so that's it. So remember, this AB will determine ABEF. AB cannot determine ABDE. AB cannot determine ABDE. AB cannot determine ABCF. So you can see this is also no. Okay, and you can see this is also no. So that is the reason this decomposition is lossy, or I can say this decomposition is not lossless right now. Okay, right now this decomposition is not lossless. This decomposition is right now lossy. Okay, now the question is saying which changes we can make individually. So let's focus on the first change. Okay, let's see whether this change, if we make, then will this decomposition become lossless or not. Okay, already this set of functional dependencies you have. Now the question is saying that you add this functional dependency in this F. Okay, so remember, if I add this functional dependency in this F, then also remember, for this R1, for this R2, the intersection, the R1 intersection R2, that will still be AB. Okay, so now what you do, you add this in F. Okay, let's add this in F. Let's add here, means D determining A, B, C, D, E, F, everything. Okay, now what you do, in this complete thing, in this complete thing, you find what is AB closure. I'm only interested in the AB closure because I want to check whether the set of common attributes in R1 comma R2, the set of common attributes, is it a super key in at least one of them? Yes or no? The set of common attributes in R1 comma R2, can it determine R1 or R2? This is what I want to check. So AB closure I want to see. Remember, AB closure will still be the same. Okay, because you can see what AB closure, AB can determine AB by the reflexive property. Then you can see B can determine EF. That's it, nothing else. Okay, yes or no? You can see that still, even after this change, you can notice that still, even with this change, even with this change, even if you make this change, then also you can notice that this R1 intersection R2 does not determine R1, and this does not determine R2. Okay, yes or no? Even with this change, the R1 intersection R2 does not determine R1, and this does not determine R2. So I can say that which of the following changes will make this decomposition lossless? So definitely this is not the answer. Not making about decomposition is lossless. Yes or no? Not making the decomposition lossless. Okay, so definitely this is not the answer because it is not making the decomposition lossless. Okay, so this is definitely not the answer. What about B? Let's check. Let's focus on this change, this B. Here you are saying that we are adding E determining C in this set of functional dependency. Here you add E determining C. Okay, then again what you do? Then again you find what is AB closure. Why I am finding AB closure? Why I am so interested in AB? Because here you can see that this is R1 intersection R2, that is your AB. Yes or no? The set of common attributes, that is your AB. I want to check this AB is a super key in at least one of them or not. Okay, so you can see what is AB closure. AB closure will be AB. B can determine EF. Now you can see B can determine EF. And notice E can determine C. Very good. Okay, E can determine C. Now notice, now you can easily see that this AB can determine ABCF. Yes or no? And what is this ABCF? This is your R2. So basically, And what is this AB? This is your R1 intersection R2. R1 intersection R2 is deriving R2. So that is the reason I can say that decomposition is lossless. Lossless decomposition. Okay, so definitely this is the answer. Yes or no? Of course, let's find the complete closure. So what is AB closure? That is ABEFC. Then C can also determine D. You can also add D. So I got ABCDEF. Everything I got. Okay, so actually you can notice that here this R1 intersection R2, it will also determine R1. It will also determine R2. But at least one of them is enough. Yes or no? If R1 intersection R2 determines R1, that is enough to say lossless. If R1 intersection R2 determines R2, that is enough to say lossless. At least one of them should happen. Very simple. Okay, let's see the third one also. The third one is saying that we are adding this B determining D, this functional dependency in this set. Okay, so what to do? Let's add here. Okay, so you can see B determining D. Now what to do in this set of functional dependency? This is the new set of functional dependency. Again, let's find what is the AB closure, because this is R1 intersection R2. So AB closure, what that will be? That will be AB. You can see B can determine EF. Okay, that will be EF. Now notice B can also determine D. So I got D also. Okay, that's it. Yes or no? Now notice one thing. Here you can see that this is your R1, this is your R2. So what is R1 intersection R2? You can see this is R1 and you can see this is R2. So what is R1 intersection R2? That is AB. Yes or no? You can see that AB is determining ABDE. Yes or no? AB is determining ABDE. So what is this ABDE? This is your R1. And what is this AB? This is your R1 intersection R2. R1 intersection R2 determining R1. That is enough to say that the decomposition is lossless. Okay, so definitely yes, this change will also work. Is this clear? Yes, this change will also work. Very good. Okay, so I hope you understood the complete analysis of this question. So in this question, I can say that these two changes will work. These two changes individually, if you apply these two changes, then they will make the decomposition lossless. Okay, so very good. And this will not work. Okay, I hope you understood. Very simple. So far, all the questions you understood? Let me know. I can see students are sharing their mistakes, which mistakes they made. Students are sharing, and that is a good thing. See, one thing I want to tell you, that you don't have to make all the mistakes yourself to learn from the mistakes. Okay, so some mistakes you can learn from others' mistake. Okay, here you can see in this chat, I can see many students are sharing after every question, they are sharing which mistakes they made, which silly mistakes they made. Okay, so from their mistakes you can learn, you know. So many silly mistakes they have made in different question, different type of silly mistakes they have made. So from their mistake you can also learn. Okay, you don't have to make all the mistakes yourself. So I think the remaining questions we can discuss in the next session. Okay, already I think we have taken 3 or 4 hour session. So the remaining questions in the next session we can discuss. Is that fine? Let me know. Okay, so let's discuss the remaining questions in the next session. Okay, so basically tomorrow means today basically. Okay, because now it is 1 a.m. right now. So I can say not tomorrow, basically today. Okay, we will discuss. Okay, the remaining questions we will discuss. So I think Sachin sir will also discuss. Okay, today. Sachin sir will also discuss. I will also discuss my remaining questions. So Sachin sir will discuss. I will discuss. Okay, I will discuss the remaining questions. So I hope you loved this session, and I hope you understood the complete analysis of each and every question. And one thing I want to address actually, there was one student in the chat. One student sent I think 20 rupees in the chat. I can see, I think, somewhere. Okay, because I was explaining, I was teaching. That is the reason I could not address it. But some student sent 20 rupees. I want to tell all the students that actually what you can do, you can just like the session. If you found that okay, this session is helpful, if you understood something new, and if you loved that, see, we are from the beginning till the end, almost no time I wasted. I was completely explaining, okay, the complete time, no promotion, nothing else. So almost 99.99% time we are just explaining the concepts, the complete analysis of each question, variations, what are the possible variations. So everything we have seen, the complete analysis, the detailed solution of each question in this session we have seen. Okay, so I just request you one thing, that to support Go classes, you can just press the like button. Okay, that will not take time. Then you can put a comment also, because the YouTube algorithm, YouTube algorithm, that that will see that YouTube algorithm will consider that okay, the person is liking, the person is putting a comment. Okay, so whatever small big comment, whatever comment you want to put, so whenever you are watching any Go classes video, any Go classes lecture on the YouTube, if you find that okay, yeah, this lecture was good, I understood something new, I learned from it, then just press the like button and put a comment. Okay, we read your comment. Okay, I have the YouTube Studio app installed in my phone, and every day I just go through the comments. Okay, so we go through your comment and it will motivate us, it will encourage us. Okay, so you can share the feedback of AIMT1, which mistakes you made, which silly mistakes you made, what did you like about this session, the complete analysis, which question did you like the most. Okay, which type of question you want in the upcoming AIMTs. Okay, so any feedback, suggestion, advice you can share. Okay, thank you everyone, thank you so much. I hope you loved this session. So see you in the next session. Okay. One student is saying मजा आया इस सेशन में. Sir, you are amazing. Thank you everyone. Your explanation is amazing. Thank you everyone. So thank you for your support. Okay, thank you. Bye. अभी डिनर करूंगा मैं, क्योंकि AIMT खत्म हुआ, ऑल इंडिया मॉक टेस्ट खत्म हुआ, उसके बाद में फिर डिनर से पहले ही ये सेशन शुरू कर दिया. ओके, तो अभी see you tomorrow. See you today in the for the remaining questions. Okay, thank you.